uh, okay. On Canvas, I'll probably have to post it to YouTube because I know how to do that. That's just as long as I'm able to get this file, I can do something with it. I'm just worried that something might, technology, I don't know what is going to happen between Zoom and my computer. But if just as long as everything goes right, I'm going to get it on YouTube, and then I'll send a link in an email to all of you.
Thank you.
But first of all, why won't this? Okay. Anyway, so all right. So let's do it that way. There we go. That'll record the full screen. I don't know what it'll do, but I wanted to make sure it was on full screen so it's recording. That's the other thing that you really won't get much of the chat in the recording either. But anyway, either way, let's do this. So, yeah, I guess to start off, right? There's so everything, believe it or not, and maybe you've realized this, is that these first two chapters are really like they could have just been one chapter. They shouldn't be separate in your head. You shouldn't have like separate ideas, and you should also, and I'm going to stress this a lot as we review here, please listen to the words we're using, okay? Because a lot of times, we might see an equation, because the reason why I say that is because we've given you a lot of equations for the same stuff. Like you have like 4 or 5 equations for like electric field, right? And you have listen to my specific, and Dr. Mugano, both specific words, okay? And when we're talking about each specific equation, because they're specific, right? Even when it comes to potential, listen to our words. Like we're never saying like this equation is potential. A lot of times we're just saying this is how you calculate it. This is how you calculate it. And it's much different to say, well, we have different ways to calculate, right? We have 1,000 different ways to calculate acceleration, right? But acceleration itself is this thing, right? And so if that's not making any sense, it will here in a second. But we just have to, make sure, like you should have a general understanding of everything. Like really, we're just talking about all the same thing here in all 3 chapters. We're just trying to talk about it in a different way. And so and let me say this as well, is that the overarching concept, and this is going to be very, very important what I'm saying here, for not just this test, this is going to be true until probably after midterm, okay? We're going to be talking about forces, electric forces, magnetic forces, blah, 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 blah. But your mind needs to be on the fields, okay? Like as we talk about stuff, the important thing here is the field. I know like it feels like, well, force is really important, but what you should have taken away from a lot of our discussions is that force is only there when you have an electric field, right? So, and it's a very important order. Like you don't want to think that like electric force gives you electric field. No, that's bad. There's an actual order here. Like if you have an electric field, therefore you have this electric force, okay? And what we see is that the electric field, right? If we want to describe the electric, I forgot to say this. And then, right? So you have an electric field, therefore there's going to be an electric force if you put a particle there. Okay, it's not always like there's not a force there if there's no particle there, right? But there's still an electric field. But if you put a particle, right, just to show a drawing real quick. So if I have an electric field, right, like that electric field's there. right? But there's no force until I throw this bad boy there. So that's why there's an order, right? Like you always have the electric field, and then where's the force come? It comes from the electric field. Okay. And those two things, right? Both of these, does everyone understand that? Remember, Dr. Duncan is like, he tests, I think all of you have had him. He tests you so conceptually, right? You all know this. So you know these things we're saying right now are like, you know what I'm saying right now. Okay. Well, and if you never had him, look at everyone and what they're saying because they'll back me up. And he tests very like let's say this real quick. I want to say this in 2 minutes here. Please, and please respond real quick and help these students who haven't had him before. Let's just do this real quick. Does he have you calculate a ton of stuff on the test? Please just answer back really quick.
No.
No. Does he? I mean, you might calculate on 1 or 2 questions, right? Maybe, right? Or there you go. Like how? Like, I mean, like actually calculate a number. Please don't misunderstand me. He asks you to now. Does he ask you to solve for equations on the test? Yeah, that's more often. So don't confuse like solving for equations and like solving a solution. Like he doesn't really ask you to put very many numbers into your computer. I mean, into your calculator, right? Like that doesn't happen too much on the test. So just keep that in mind. Yeah, Levi, you can just speak up, my brother. Go ahead, my friend.
Well, he like tell us what to solve in terms of because I was going over a lot of the lectures and he's just like solve for electric field and then he uses like capacitance and then doesn't tell what you're solving in terms of.
So again, and I think everyone can back me up, and then we got to get back on the review. I wanted to just take 2 minutes here, okay? So let's if you have more questions, just send me an email. But the nice thing about the test is what everybody is that it's multiple choice. So there's less of guessing how to solve the question, right? You can look at the answers the way he's like, he'll ask you a question, then you can look at the answers, right? And you'd be like, oh, he wants me to solve for like if those answers weren't there, it might be a really hard question, right? You'd like, I don't know what he wants me to use. I don't know what he wants me to do. But the answers a lot of times like leads you to the questions, correct? Or no, am I incorrect about that? Please tell me from a student's perspective.
No, you're right.
Okay, so there you go. So that's what you're going to have in your back pocket to answer that question. Like you're like, do I need to know the capacitance? I'm telling you, man, you're going to look at the answers and you're going to know how to answer the question. Okay, if you studied, you'll be like, I know what to do here, right? Because the question. Okay, let's get back into the review. Okay, but those of you who I wanted to do that for you. Okay, so he does, and then again, please just answer this just a yes question, and then we're back into this. But does he directly? I mean, might change a sign, might change a direction, but overall, he's picking from the work from the lecture slides, the clicker questions, worked out questions from the lecture slides, and the worksheets. Correct? And a lot more like it's he leans towards the worksheets a little bit more, correct? Or no? Do you not feel that way? Okay, so just keep that in mind. Okay, let's get back into this review. Now you know. This is other students telling you, not me. Okay, so what these two things are where it's at, but it's really about this electric field. And right after this test, we're going to start talking about magnetic field. It's going to work the same way. So just make sure that in your head you have like this overall theme needs to be about electric fields, okay, or magnetic fields in general. And those fields, whatever field is, magnetic field, electric field, they then give us some force, okay, because of the fields there, just as long as we put a charge there. Okay, this is going to be true for magnetic fields, all right? So it's something we have to get down in our head and really understand. These two values right here, they're vectors. Okay, and as you well, maybe there was a lot going on last semester, right? But vectors are great, but vectors are very hard to work with. And so I don't know if you picked this up last semester, and it's okay if you did. I'm just going to tell you it's not something you need to know for the test, but it helps you understand this what we're doing here in this class right now. Is that what happened is that we introduced you to Newton laws, and then right after that we introduced you to energy. And the reason why is because we wanted to give you a way to look at force without looking at it in terms of a vector, right? Because work lets you look at force as energy, not as a vector. It lets you look at it as a scalar value, right? It's okay if you didn't take that away, but that was the thing. We were trying to make our lives easier. We were trying to say, hey, okay, forces are, if I got 1,000 forces at one spot, man, that's hard to work with. But if I can just look at the changing kinetic energy of that object from one place to another, like that helps me look, like I can look at, I don't have to look at the vector. I can just look at the scalar value of the energy, and that'll tell me something about the forces there, right? And so that theme never goes away. That is true here, okay? And that's all we're trying to do. So when we talk about potential, we're really just trying to talk about potential or the electric field in terms of a scalar value. We're trying to make it easy because electric fields are hard to deal with as vectors. If I just have two charges hanging out or something like this, oh my goodness, it's so easy, right? But imagine if you have a spot that has like 1,000 electric fields and they're all at different angles. And again, this is 3 dimensions, right? It gets nuts because you have to break all those vectors down into components. Anyway, and we're going to do that here in a second. So, but what you should know is that when we start to talk about these things, potential and then electric potential energy, right? We're just trying to give some sort of like scalar understanding to these things, either force or electric field. Okay, and then like I said, it's kind of the same thing here. So we're going to write it in now. But like I said, you don't get a force. Okay, you don't get a force until you add a charge. So you have this electric field, you add a charge, and that's the way we then have some sort of electric force. And it's the same thing down here. If you have some sort of potential, but then you add a charge within that potential, then you end up with some sort of potential energy in that system. Okay, so this is a really good graph to just have in your head and study because it helps you understand. Like I said, we could write scalar going down. We could write vector going up. I know this seems very mathy, everyone, but please, this is what we're actually trying to tell you right now. This is what we're trying to say. Okay, we said a lot of stuff because we're trying to, and again, if some of you want the details, like, man, where's this stuff coming from, Carl? Please rewatch his lectures. Okay, like he'll describe as much as he can. I mean, this is energy. Yes, energy is a scalar. He'll describe as much detail as you need to know. Remember, this is an introductory physics class, so even us physics majors, like, we have to take electrodynamics to really understand electric fields and magnetic fields. We don't get it in our introductory physics 2 class. So if you have those deep questions, please, like, save them, ask us in the email, or please watch his lectures because he's trying to give you those details. But then at the end of the day, this is what he wants you to know. This is what he's testing you on, is what you're looking at in front of you on the screen. Does that make sense? But he doesn't want you to know this thing comes from magic, because a lot of it sounds like magic, right? These charges pushing on each other, nowhere near each other. It's like, what's this magic going on? So he's proven everything to you. But at the end of the day, it's like, no. Look, we're just trying to make sure you understand what electric field and electric force are and how potential and potential energy relate to those two things. Does that make sense? Okay, because that's the thing. Like, a lot of us, and we're going to talk about it a little bit more, but a lot of us get like these two things right here very confused with each other because they're not the same thing, right? They're not the same thing. They sound very close, but they're not the same thing. We don't get students confusing electric field and electric force very much. It's these two that get confusing. So when we get to that point, we're going to make sure that we have what I did for you all is I went back to my old physics days and I actually found a few graphs of potential. So you know what I've been drawing this picture for you, and I don't think it's doing it justice. I want you to see what potential actually is, because when you see it, you're going to be like, oh my gosh, that's what you'll always have that in your head. You'll never get it confused with potential energy. Okay, because anyway, when we get there, you'll see what I'm talking about. All right, but we're going to start with the electric field and electric force, because those are the real players here. Okay, So before we get into those real quick details, because again, we don't have, I just have an hour here to try to review all this stuff. I'm trying to review 2 chapters at once, essentially. You can see that. Is that, but again, as we work through the worksheets, we're going to definitely, we'll cover some concepts, right? So don't think like this is it, but it'll probably mainly be done through the worksheets. So one thing, and again, some of you I've met with, and I don't know, I will admit, like, I wish I could spend more time with you and really show you how to use this. I'm going to write it down and we're going to try to use it as much today. But this is a very, very helpful graph, okay? Like, please write it down, and it's almost important to memorize. Like, I didn't make this thing up that I'm drawing for you in front of you. It was made by a Nobel Prize winner in Boulder, okay? He's like, he teaches, and this is like this thing that he gives to all his students for his test. He's like, look, if you have this picture and you write this picture down on your scratch paper right before you start the test, you're going to have a lot of the answers in terms of concepts, right? I mean, there's details that you'll have to still memorize, but in terms of electric force and electric field, potential and potential energy, just the concepts associated with them, this is everything. And those of you who I have showed, I mean, does this thing actually help? Like, if you have this thing sitting in front of you when you're answering questions, does it actually answer questions for you? Has anyone tried to use, see? And so that's the thing, okay? This is something not to just like write it down and then like put to the side, okay? I'm telling you, you want to have this thing and you want to memorize this picture. It's not going to give you 100% of the answers, right? Because that would be a really messy picture. But this gives you so many answers to a lot of questions. And all you have to do is look over at this picture instead of looking through it, flipping through a ton of notes, okay? And so, first of all, we all know that the electric field, right? I mean, this is saying a lot of things, and if we need to go into detail of it, we were. I didn't have too many plans to do that, but we know that the electric field has an outward direction from the positive and an inward direction from the negative. So in this case, when they're sitting next to each other, it looks like the electric field goes from the positive to the negative, right? That all makes sense to everyone, right? But we still know that the positive and negative sides each have an individual electric field. It's just when they're in this situation, they end up looking like this. Does that make sense? Okay. Now remember, this is a concept that's, like I said, these can be 2 chapters here. Okay, and we're going to try to get into a little bit detail of this, but this is where how you should see it on this picture for the concept that it is, okay? Every time you have an electric field, okay, and we'll dip into this concept later, not right this second. You have not a potential, but a change in potential. Okay, if you don't have a change in potential, this is a concept, you can write it down. If you don't have a change in potential, you don't have an electric field. Oops, what the hell am I writing? Right? So what does that mean? That means if you have a potential, that doesn't mean you have an electric field. You have to have a change in potential, okay? Changes in potential, another way to say that sentence up above is changes in potential give you electric fields, right? In fact, there's this equation that tells you that. Okay, it's not potential. We never, ever, 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 ever wrote this equation like this because it's not true. Okay, this equation is only equal to the change in, it's only the change in potential energy, and that's a concept right there. That's a concept telling you that it's not, I should have left that up, telling you that this is not there. Okay, it's not potential. Potential does not give you an electric field. It's changes in potential, right? And if you want to see it directly, right, you get this equation, which is going to be on the worksheet here in 2 seconds. that directly lets you link the changes in potential to the electric field, right? So it's not potential. You will never have an equation that is potential is equal to electric field, because V is a totally different number. Change in potential is not, it's not potential. Just like velocity isn't changes in velocity. And this is such an important concept to get down in your head. It seems like, yeah, I know that, Carl. I know they're not the same. But if we tell you that the potential isn't changing, you should already have in your head that there can't be an electric field there. We'll tell you, hey, there's a potential here, but it's not changing. You don't want to say, oh, there has to be an electric field because there's potential. No, it's changes in potential that gives you the electric field, not potential. Okay, and that's a huge concept. So if you don't have, what the hell am I erasing stuff? If you don't have changes in potential, no electric field. Okay, very, very important. Now, this doesn't, the electric field can be constant or not. Okay, it can be constant, it can be changing. Okay, that's irrelevant. Okay, but if this is present, this has to be present, and vice versa. Like we might just say, oh, blah, 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 there's a change in potential, blah, blah, blah. You should write in your head, go, oh, electric field. Okay, does that make sense? Okay, because that's what this is trying to tell you. All right, and remember, what does it mean? We'll get into that. Well, let me just ask you right now, what does it mean to have a change in potential energy? I mean, sorry, not change in potential energy. Crap, I just said the wrong change in potential. You're just going from a very what potential to a very what potential?
High to low.
High to low. It's like that simple. Or low to high, right? It doesn't, I kind of set you up there for the high to low, right? But it could go either way. But right, low to low doesn't get you anything. High to high doesn't, that's a constant, like you can have those things, right? But high to, it's those high to lows. Let me just show you, because I would, let's try to make this as I thought I could just add a picture. Maybe not. Well, that's a bummer. Maybe I won't be able to show you. I thought I could just add a picture here, but maybe not. Anyway, so oh crap, I just lost everything. Let me just show you real quick. I'll be able to get that stuff back. I just want to show you real quick. It's a good thing, like I kind of found this out, because so that's what there's the picture of potential. Okay, I'm glad I did this before I had too much written down, because I just deleted everything that's on there, but I'll rewrite it. Okay, that's an example of potential. It's literally these peaks and lows, and like this, like I want this to go away. What is going on here? Oh no, really? What the heck? Why is it not showing you? Can you see it now?
Yeah, I can see it now.
Okay, what the heck was that about? I pressed that. Anyway, okay, there you go. That's a good picture of potential, right? Like, it's just these peaks and lows. This is literally like from my days. This is how we see it as physicists, okay? So when we talk about potentials, and more importantly, a change in potential, right? Do you see how there's a change in potential here? Because we're going from a very high potential to a very low potential here, right? That's literally what we're doing. And right here, right here, that's where, like, we have zero potential. You could think of that as like, you know, sea level or something like this. And then those one's a mountain and one's a hole. Okay, and this right here represents a positive charge. So let me get rid of this. And this right here represents a negative charge. Okay, and they can be, you can look at these things like in individually, like they don't, this is a dipole, right? As you can see, this is a graph that I made of a dipole, but they can be like separate, like that can be just a positive charge, and that's just, so if I just have a positive charge, right, it's going to have potential. Why? Because it has this essentially this increase and this decrease. Okay, and the same thing with the negative charge, right? It has this increase and this decrease, right? And you can do that on either side, right, of either of these charges. So as you go towards the peak, there's this constant, right, change in potential right here, because you're getting higher and higher and higher, lower and lower and lower. And the same thing right here, just having a negative charge by itself, it's going to have its own change in potential, because you're either getting lower, 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 or higher, higher. You're getting more and more out of the hole. And that's exactly why these things have, oh, that's not a good color, electric fields, right? We know that individual charges have electric fields, right? But we can recognize those, because that's how I made this graph, is that I can recognize that charge is there. I didn't know these charges were there. And I found them by finding their potential. And then I knew that there is an electric field that was sourced right here at this point and right here at this point. And then I knew that that's where the charges were. Okay, so that's how we use potential. But this is, I wanted you to have a picture of like what potential is. I think I have, I'm not going to write and talk too much, but this is actually another really good photo. As you can see, remember I told you, can everyone see that?
Yes.
Yeah.
So remember, we keep telling you it's the great, and Dr. Yungana, there's questions on the worksheet we're going to talk about, and you'll see what he's talking about, where we're referring to this gradient there. You see that where it says normal, like it says the gradient, like increasing and right? It says it's increasing in that direction, it's decreasing in this direction. And that's what we mean by the potential is just a gradient. See this right here, right? And see, you can see it's measured in volts. And this right here is just, it's a, you might be saying, well, what is it the gradient of, Carl? It's the gradient of the electric field. Okay, so like I was just showing you, we know that these electric fields are here, and these electric fields, right, they have a gradient to them. And that's how we're able to we don't have to look at the vector side of electric fields. We can just look at the scalar side of, which is just the potential, and look at the gradient, which the potential is just the gradient of the electric field, and it lets us find the sources of the electric fields at certain points. Is this making sense what I'm saying? Here's another, so this is a 3D picture of it. Okay, this is the last one, and then we're going to move forward, but I want you to have a picture in your head. Like I wasn't making it up when I said these things are peaks and troughs. It's like I wasn't just trying to, remember I kept drawing that picture for you, that those peaks and troughs in SI. Like I want you to know I wasn't just like trying to make a picture to get you to understand something. Okay, it's this. It literally is these peaks and troughs, okay, where again, like this, right, this is a negative charge, right? Negative charges are always like literally represented by holes in the ground, or essentially the potential is essentially, this is what we mean by a negative potential. This is what we mean by a negative potential, because it's literally negatively, right? It's negative, it's into the ground, right? And this is literally a positive potential, because it's literally like positively out of the ground. That's why, that's how these get their signs. Okay. And this is why, this is a concept. This is why I showed it here, because we're going to write it as a concept. This is why the potential, okay, this is going to be the big takeaway here. This is why the potential always is higher. It doesn't matter the charge, right? If I put a a positive charge in here or a negative charge within the electric field that's sitting next to these right there, we know that there's an electric field here, right? So if I put a positive or negative charge in there, it doesn't matter because the potential, let me do those in a different color. The potential doesn't matter about these charges. Now we can use those charges to describe it, and I'll show you what I mean here in a second with that equation. But the potential itself, right, is there whether we have those charges or not. Does that make sense what I'm saying? Like when I take away those charges, the electric field's still there, right? And this is kind of deceiving actually. Let me draw this, make a little bit more sense, because actually the negative charges is come on, right? The negative charge is right here. The positive charge is right here. This is a little deceiving how I have it. But as you get closer to the positive charge, the electric field increases. And this is the gradient associated with that electric field at that point. Like, does that make sense what I'm saying? So it's probably better to say the positive charge is right here and the negative charge is right there. There we go. That's 100% accurate right there. Okay, so they're sitting across from each other, right? And there's an electric field between them, right? Whoa. And so that's what we're trying to describe here, right? There's an electric field there between those two charges, right? And so that's the whole entire picture. All right. And this is why the potential always increases in the direction of the positive charge, right? It doesn't matter like what we're saying, right? It doesn't matter like if I have a positive charge or a negative charge, like in this electric field between those two charges, because there's always an increase near the positive charge, right? There's always like a positive gradient near the positive charge. There's always going to be a higher potential near like the positive plate. Like this could be a positive plate here. Instead of two positive charges, this could be, this might really help you actually. This could be a positively charged plate. This could be a negatively charged plate. And so the electric field sits in between those two plates, right? So as you can see, the potential is always high, even no matter if I were to take a positive charge and put it in this electric field, it doesn't matter what charge is in the electric field between these two plates. The potential always increases near the positive charge and always decreases near the negative charge. Do you understand what we're trying to tell you now in class? We say like it doesn't matter the charge, the potential always is highest near the positive plate and always lowest near the negative plate.
Yes, quick question.
Mm-hmm.
I get it. And the fact that it doesn't matter what the charge of the molecule is, it's just dependent on the plate. But in this case, in this specific example, since we were using a positive, the likelihood of it increasing in potential as it moves towards a positive plate would be pretty slim, right? Because it's a positive charge and it would repel.
No. If I mean, you're thinking about repulsion, which is great, but what you should think, because when we have a positively charged plate in a capacitor or a battery,
Mhm.
what did it take to get those charges there? We had to push them on the plate, right? They
Yeah.
if we would have waited for it to magically happen, like they wouldn't have done it. There would have been too much repulsion, right? But we had a
Yeah.
force charge onto the plate. So, I mean, if I'm trying to get a positive charge, a positive charge closer to that plate, I'm gonna have to push it.
Yeah.
I'm gonna have to push it, right? But I could do it. And if I started to push that positive charge towards that positive plate, the potential of it would increase. Just like if I were to push a negative charge towards that positive plate, the potential of it would increase. Either one of these charges, if I push it towards the positive charge, it increases because the potential right there, because of those positive charges, increases, it peaks. Be always near a positive charge, because what happened, remember, and we've explained this to you, potential is just a way that we were trying to explain the electric field because it got too complicated as a vector. So we said, hey, can we start to look at potential and understand or understand these charges in terms of potential and things like this? And it's like, yeah. So we made up, we said, how can we do it? And actually there's this thing mathematically, it's a mathematical thing that we take from calculus, and it's called the gradient and the curl. And when we take the gradient and the curl of the electric field, we get the potential. And so the curl is always 0 for an electric field, which leaves always just a gradient left over. And so that means the potential is really just this gradient. It's this mathematical thing we made up. And then we started making these graphs based off that math thing that we made up. but this is what it means. So does that make sense?
Yeah.
Okay, cool. And everyone else, does this make sense? Okay, hopefully this helps you, because now when we ask you in terms of concept, you need to always have in your head that the potential is always highest. Well, hold on, let me draw it. I want you to tell me near a pot. Well, I'm going to say it again, but then I want you to tell me near the positive charge. It doesn't matter. It doesn't matter the charge inside the electric field between the plates, right? It's the potential is related to the thing creating the electric field, right? I think that's what we saw, right? And then I could throw, any charges in here, right? And that doesn't change the fact that the potential is higher near the positive plate, lower near the negative plate, right? And that's what I showed you in terms of the picture. But now you're going to tell me in terms of just looking at this. So these are the things. Well, I didn't have that electric force thing written. That was the next thing to write. So change of potential, electric field. No change in potential, no electric field, okay? And we see why the change in potential matters, because if there's no gradient, right? Anyway, that's getting too deep. And so we know that if we were to then place a positive charge or a negative charge in this electric field, that it's going to have an electric force applied to it, but it's not going to be applied in the same direction, right? So this is telling you a lot again in terms of concept. This is telling you that this is universal, everything that's on this picture, okay? So positive charges always move in the direction of the electric field. Negative charges always move in the opposite direction of the electric field. Okay? That's very, like, you want to write that down and memorize, because we might just tell you, oh, there's electric there's a positive charge with an electric force up. Which way's the electric field? Who can tell me? I got a positive charge with the electric force up. Which way's the electric field? Yeah. Okay, I got a negative charge with the electric force towards me. which way is the electric field? So now the electric field's towards me. Away. Oh man, I thought I was gonna trick you there. Man, you guys just are so freaking smart, man. Jeepers creepers, there's no getting nothing by you. Okay, so amazing. Great job. Okay, so I think we're all starting to really get this idea down. And so the next concept that's on this picture that you should memorize and literally write this down, it takes 2 minutes to, once we have this picture completed, you'll be able to write it down in 2 minutes, and you should just write it down right before you start the test so that you have it to refer to on the test, right? You can't bring notes in, but if you memorize this, jot it down right before you write it. You didn't bring any notes in. It's something you have in your head, right? It's not on a piece of paper or anything, right? You're going to write it down from your memory, but that's like writing an equation down from your memory. We don't tell you can't do that. Okay. It's not a good idea when you don't tell you can't do that. So then the next concept that's on here is that the potential energy. So we know for a positive charge, the potential energy is always highest near the positive side and lowest near the negative side, right? And for a negative charge, we know the potential energy is always lowest, not potential, this is potential energy, okay? The potential energy is always lowest near the positive side and highest near the negative side, okay? So again, there's more than just repeating that, just saying, oh, it's higher near the positive. No, what you need to be seeing is that, because as you see from the worksheets, he asks you, is the potential increasing? Is the potential decreasing? And those answers come from this picture. You say, oh, okay, so if I have this positive charge and it starts to move towards the positive plate, its potential energy is increasing. If it's moving away from the positive plate, its potential energy is decreasing, right? And for a negative charge, if it's moving towards a positive plate, its potential energy is decreasing, right? And if it's moving towards a negative plate, its potential energy is increasing. And that kind of goes on the point that was said earlier. And you want to kind of think this is that if these charges were left to do what they want to do, if we don't put any force on them, then they naturally move from a high potential to a low, right? To a low potential. Negative charges are moving from a high potential to a low potential. Positive charges are moving from a high potential to a low potential if they're left to do what they naturally do. But yeah, if I push on this thing, I'd have to apply another force. I could push it back. I mean, yeah, it'd get harder and harder, but I could do it, right? I could do it, right? It would take another force. So when we say that particles always move from high potential energy to low potential energy, keep in mind that's when they're free to do the movement on their own. We can start pushing things around, okay, with another force, okay? So all this stuff is just in terms of just a particle and an electric field, right? And then the last concept that's on here that you should just, again, always have in your head that we just talked about over and over and over and over is that no matter the charge in the electric field, so we don't care about the charge in the electric field, the potential is always what? Highest near the positive charge and what? Lowest near the negative. It doesn't matter the charge in the electric field, right? This charge doesn't matter because we know that the potential is coming from these plates out here. Like that's what the potential is related to the electric field, not that charge in there. But students get very confused because they're like, Carl, dude, then explain this to me, my brother. Because I'm telling you right now, man, this sure looks like change in potential energy. I have to have a change in potential energy to have a change in potential. So that means if I don't have a change in potential energy, there's no change in potential. Is that true? Think about everything we said. Do you have to have a change in potential? Think about those pictures we just looked at. Do you have to have potential energy or even a change in potential energy to have potential or a change in potential? Either one. No. Then what the heck are these equations doing, man? What's up with these equations? What are they trying to tell us then? Because if that's not a necessary thing, I look at these equations and say, oh, oh man, if I don't have a change in potential energy, there's no change in potential. But the thing is if I just have an electric field like this, okay? If I have an electric field like this, do I have a change in potential?
Yes.
Yeah. But I don't have any particles in there, right? I don't have any like potential energy essentially within the field, right? Within the field. Sorry, I got a question. Hold on one second. What is the clear cut meaning behind potential? So it's potential energy. So potential energy is just the energy associated with the field, which is really just coming with like how much force that field can produce. So that's what this picture was. Okay, so an electric field gives you an electric force, right? But we can describe the electric field in terms of potential, and we can describe that force in terms of potential energy, right? And then we know that if I add a charge to the potential, I get potential energy. And if I add a charge to the electric field, that's what's actually giving me the force. That's what's actually giving me the potential energy. Does that make sense? Because as you saw, if I have a positive charge and a negative charge, or let's not even do that. That's too complicated. If I just have a positive charge sitting by itself, right? Is there any potential energy here? Huh. Is there potential? Oh, look at you all go. Is there a change in potential? So there is potential. Is there also a change in that potential? Remember, changes in potentials have to do with going up or down the mountain or in and out of the hole. If I just move from here to here, that's like so this right here, right, in terms of that 3D model, this would be considered an equipotential surface right here, right? But every level is a different, every level is a different potential, right? Every level is a different potential until you get right here when you're at 0. But that's really far away from the charge, right? When you're far away from the charge, the potential goes to 0. Remember here in that concept? That's again where this is coming from, this picture, right? But it's as you either increase or decrease down here, that always gives you a change in potential, just as long as you have some sort of you're going from some sort of high to low. Okay, that always means you have a change in potential, and you just have a potential because of this charge hanging out, right? But there's a change in potential because there's an actual gradient here, and because there's a change in potential, we have this electric field, right? Does that make sense? Is this helping putting things together?
Yeah.
So there's no potential energy here right now, right? So we can have, so when we talk about this equation, this is where I said, listen to the details of our words. We're saying this is a way to calculate it. Like it's a way to think about it. Like I can calculate the change in potential if I threw a charge, like let's say that I didn't know anything about the charges out here, right? But let's say I wanted to know something about the change in potential in a certain space. Let's say I didn't know it wasn't a charge. It's just like a space in the, right in the middle of like sitting right in front of you. I wanted to know if there was an electric field right in front of your face right now. Well, there's no source charges to look at, is there? I can't look, right? Look. Are there any source charges in front of you, right? But there's an electric field in front of you. And how would I find that out? Well, I could throw a charge in front of you. Now it'd have to be really small, so because the electric field isn't super strong, but and that charge would respond. And I would look at how the change in potential energy of that charge, I would say, oh, let's see how that potential energy of that charge changes as it moves. Because I know when that positive, when I throw that, if it's a positive charge that I throw in there, it's moving from the positive side to the negative side automatically. There's no other forces there. It's just the electric field that's there. It's moving from the left to the right. And when it does that, there's a change in potential energy. It's gone from low to high. And once I know that, once I know how much change in potential energy per charge, I can figure out the change in potential. I can say, okay, well, the change in potential is going to be based off of the change in potential energy of this charge, since I can't look at the electric field. But then once I have this, I can say, well, now that I know the change in potential, I can figure out the electric field that's there, even though there's no source charges around me. Do you see how that works? And that's where that equation comes. So it means a few different, right? There's a lot of different equations for changes in potential. And a lot of them are really just trying to show you different ways of how we calculate it, how to calculate it. Okay, because as you saw, if we're going to try to talk about it as the thing it is, we're going to be talking about it as these mountains and these holes in the ground, right? Which are helpful to know. It's helpful to know, right? But you should know that, there's a lot of different ways to figure out those peaks and troughs, right? We could look at the change in potential energy of a particular charge, or we could look at, oops, that was wrong. Or we could look at just like, if we know this, if we know the electric field, right? Then we know that however far away we are from that electric field, that's also going to tell me what my change of potential is, right? Because this helps me calculate it as well. So, right, because you look at these equations, be like, how can this equation and this equation give me the same answer? They don't even look like the same thing at all, right? And it's because how we're choosing to calculate the change. We can use the electric field. That's one way to calculate it. Or we can use like the change in potential energy per charge. Does that make sense? I'm kind of sticking on potential because I know that's where all of you really kind of get a little, like, trust me, it's an abstract idea for all of us, everyone. It's not just you all. Anybody, every time we have to introduce potential, it's an abstract idea. I think I've discussed this with some of you, is that potential is abstract as acceleration. I don't know if that makes sense to any of you. We don't have time to discuss that right now, but anyway. Okay, so it's been an hour. We talked a lot about potential and potential energy. I haven't talked too much about the equations, but like I said, I think a lot of the worksheets are going to cover some of the things. Okay, now the one thing that aren't on the worksheets at all, and I haven't discussed yet, is just like how to work our way through a circuit, like parallel versus resistant, I'm sorry, parallel versus series. And so I'm going to go through these worksheets, okay, and then try to answer, or let me ask you, do you want to talk about the circuits real quick? Because that was the one thing we weren't able to make it to, and that's the one other really big concept that you need to understand before we move on to try to solve the worksheets. Or do you want to just get on the worksheets, and do you all have a good, is the parallel series thing pretty straightforward? Because some of you might be going like, I actually, that's the one thing I do understand. That wasn't actually that hard to understand. It was everything else. So, but if not, please be honest, let me know. I'm getting more, so you guys can see it in the chat. I'm getting more circuits, and it won't take very long. Okay, it won't take very long. Let's just do it real quick. Okay, let's just do it real quick. It won't take very long. I think the worksheets are a lot easier than I think you're expecting. Okay. I don't know what he's gonna ask you. I like specifically, like, I mean, yeah, but it could be something like that. Again, like we said at the very beginning, please like pay attention, because that was actually pretty important. Is that, remember we said that the uh you know the questions he's gonna throw at you. It's not a guess. We've had that discussion. We don't have time to have it again, okay? You know, we showed you so you know the questions he's going to throw at you. They're from the worksheets and the lecture slides. Okay, so you don't have to say, is he going to throw a question at me like this? You know what? He totally, like, if it's on his lecture slides, then the answer would be yes. If not, then the answer would be no. Okay. And yeah, I think that's what he does on his lecture slide. So literally you can use his lecture slides as a almost direct guide. Okay. So if he didn't ask you something nuts on there, he's definitely not, if he kept it to 2 resistors, that's what he's going to do. And also keep in mind conceptual too, probably, right? He asking about the light bulbs and stuff. Okay. So the thing we just need to know, okay, and if we got to go deeper, then just tell me, but right, let's make sure. So if series, right, versus parallel, okay, and these are just resistors, right? So first of all, like, that's right, just so that we have a picture of them down in our head. Okay, that's what they look like. Okay, this is just a quick review. Again, if you need details here, send me an email. We can talk about it then. Watch his lectures. Right, he goes through the details of these in his lectures. You can watch those as many times as you need to, but this is just to cover the concepts that you should just have after listening to everything that he's expressed to you. So we know for resistors in series, right, the current stays the same, right? It doesn't change. Which means as the current moves through these resistors, it doesn't change. Okay, versus down here for a parallel, when we hit that thing called a junction, the current splits. So what we say down here is current changes for parallel, because the currents, in order for resistors to be parallel, they're gonna have to be related to some sort of junction, and at that junction the current will always split. Does that make sense? Everyone okay with that? If not, ask questions. Cool. So the next thing in terms of concept that you need to know is that the potential, right, for series, changes. And so what does that mean? That means that as the current moves through the resistors here, right, the potential is going to change here, which means that it's going to come in, high, and leave with a lower value. I'm not saying it's super low. It's just going to be lower than whatever the heck it came in with, right? And then as it goes into this one, it's going to come in higher. I mean, it's going to be higher than whatever it's coming out this end, right? So we can see that as the current moves through the resistors, right, there's going to, absolutely. So the sign just depends on the way that you're moving through. Okay, and let me say something here real quick about this, because this kind of goes back to the discussion that we just had earlier. Okay, is that here now, when we talk about changes in potential in these resistors, can anyone tell me how we're talking about, what equation would be the best equation to refer to the change in potential as they move through the resistors? So Ohm's law is great. That's definitely going to tell us something about the change in potential. Okay, that's definitely one. Is there another one that will also help us describe the changes in potential there? And this is going to be on one of the worksheets. This is why I'm asking. So that's where this one is super helpful, because when we talk about changes in potential here, it's hard to look at it in terms of electric field or anything, because what's really happening is that the charges are being pushed with the electric field at the source, right? So what's happening is as they move through here, their change in potential energy is really directly coming from, their change in potential is really directly coming from their changes in potential energy per charge. Okay, so this one actually is more like earlier we were saying a few things, right? So it depends on how we're trying to describe changes in potential, right? We're saying, hey, there's a lot of, this is messy, but we're saying, hey, there's a lot of different ways to describe changes in potential. And it's really, when we go to look at these equations, we're gonna look at them based off the situation. Sometimes it's more appropriate to describe, oh, my pen shut off, to describe changes in potential this way. Sometimes it's more appropriate to describe changes in potential this way. Okay, so it just depends. And here, right, it's not really good to look at like distance from electric field and things like that, because literally what's happening is that these charges are literally losing potential energy. They have to spend energy to make it through the resistor. So they're literally losing potential energy because of that, not because just, how they are in relation to the electric field. They're actually having to do work. Does that make sense? To make it through the resistor. So if the charges have to do work themselves, then this directly describes the changes in potential energy as they have, changes in potential as they move through the resistor. Because they're literally losing, they have to do work. It's like moving through a tight hallway in a resistor, right? It gets hot in its way, but it's harder to move through a tight hallway than it is. Again, trying to maintain it, because this current has to maintain drift velocity. That cannot go down. They can't slow down when they go in the resistor. So that means it's like, imagine like you're running through a hallway, no one's in it, and then all of a sudden there's just this group of people and you can't slow down. You have to keep running at the same speed. And so think about the amount of work it would take to stay at the same speed you're running down the hallway with no people, and then trying to run through those people. That's essentially what the current's doing when it goes through the resistor. So then does the potential increase as it goes better? It does, but that's because now that's different. That's because literally the electric, now the battery has its own electric field, right? And capacitors have their own electric field. So they'll also do work on the charge, right? So that's different. So that's the great question. It's the same thing that's happening. Batteries increase the potential energy of a charge. They totally do. But that's because of the electric field. The electric field's now doing work on the charge. Here, the resistor's doing work on the charge. So there's a change in potential energy. But inside a battery or a capacitor, right, it's the electric field that's causing the change in potential energy. Does that make sense? Great question. Great question. Great question. Great question. No. I think everyone, this is complicated stuff. Okay. And make sure, please, after the test, we got it. This stuff gets kind of really tricky. Okay. We haven't hit the tricky part of the semester yet. How does he feel work when a charge isn't going through a resistor? Well, keep in mind the wire itself, again, great question. So the wire itself holds the electrons, but it's being pushed. So remember how I explained to you, and this is how we literally look at it in physics. Okay, remember I explained like current is more, it's better to look at current in terms of like fluid flow. So remember, like you had to have a larger pressure over here and a lower pressure. Oh, that's drawn the wrong way. And a lower pressure over here. Let's try these better. In order for there to be water to flow this way, right? It had to do with what? The delta P. The change in pressure is when there was flow. If there was no delta P, if there was no change in pressure, if the pressure at one end of the tube, if P here, right, was equal to P here, well, they're equal and opposite. Those are in equal and opposite directions. The water's not going to flow this way or that way. Both ends are pushing on the water in this tube with the same amount, so the water's just going to sit there, right? So it's this changes in pressure that allow for the flow of water. Well, what the hell? Sorry, what the heck does that have to do with current? Well, it works the same way. See, there's electrons in these in the wire alone, right? And what happens is that there's a very high potential over here, and there's a what over here, a very low potential, right? So what happens is that it's this change in, right, there's this change in potential, right, that happens there that essentially leads to the push. Just push. This is why the electrons just move through the wire. But remember, these two, this high and low end is actually happening right here, right? This is the high, this is the low, right? But it's because of the difference that it's essentially there's a high push here. So there's no electric field necessarily. It's just pushing on the electrons on this end, and that's just pushing them through to this end. Does that make sense? And it's due to the change in potential within this battery right here that causes the push. And that's why we call this an EMF, like an electric motive force, because it's working like a force. It's working like a push to the current. Okay, that change in potential that the battery supplies is essentially working as a, just like I'm showing you right here, working as a push to push the current through. Okay, and then as the current, as the current moves through, right, if it has to move through the battery, there's going to be changes in potential due to moving through the battery, but also because there's this push through here. If there's some resistor sitting here, there's going to be some change in potential in that resistor due to some change in potential energy of the charge itself. But this right here is the EMF, and it's causing the color. It's causing the push for the current, right? So that change in potential is there for the push, and then any other changes in potential that we see are coming from like the amount of work that the charge would have to do to make it through the resistor as this source continues to just pump, push the electrons through the system. Does that make sense? This is pumping. This is the pump here. So there can be, it's just that's out of the scope of this class, Levi. Okay, we're not talking about it because there's something that we call internal resistance and all these things that we're not talking about right now. And I love your questions, my friend, but they are, and they come up, in the other class, but really not even so much neither, but you really get to take it to circuits class where you get into that stuff. But yes, at the end of the day, like we got to look at the internal resistance of the battery. We got to look at the internal resistance of just the wire itself. Like, there's a lot more going on here, okay? But we don't want to make, this class isn't trying to be complicated. You guys aren't going to go build, I mean, if you want to, please do, but that's not the point of this class, is to teach you how to build a circuit. We're just trying to give you the point of the circuit chapter is just to make sure that you have a place in your head of application for electric force and electric field and electric potential and electric potential energy. That's the only point of this chapter. Does that make sense? Cool. Is everyone cool with what I said here about the push and the change in potential with the battery and why we call it an EMF now? because it literally works as a push, just like the change in pressure works as a push to push the fluid through a pipe. The change in potential in the battery works as a push to push the charges through the wire. Okay, and it's the battery itself that's giving, since the battery is the thing that's pushing the charges, it's the thing that's giving the charges the potential energy, right? So that's why the charges have potential energy to spend in the resistor, because there's this push. And so if the battery's pushing, it's doing work, and we know work is potential energy, changes in potential energy. So there's this push, it's pushing, it's giving the charges energy, and the charges have all this energy because they're moving with this drift velocity, and they're just chugging along through the wire, and then all of a sudden they hit the resistor, and they're like, oh, we got to keep going. And so they go through the resistor, but they lose a lot of energy, but that energy is coming from the push from the battery behind them. Okay, cool. Please ask questions if you need them, okay? So that's why both of these equations are actually pretty appropriate. Now what we can do is we can just when we look at the resistance, that's essentially looking at like how much work, right? There's an equation directly related to resistance where we could find the resistance based off how much work the charge has to do to make it through the thing. Okay, you guys, I don't think we give you that equation, but there's one that exists because of that reason. Like that resistance is directly related to how much work the charges have to do. And that's exactly why if charges get in this situation right here where they have to split, they will go through the path of least resistance because they don't want to spend a lot of energy. So if this has a really high, let's say this is like 10 ohms, and this is like 1 ohm, most of the current's going to want to go through the 1 ohm. They're like, why the heck would I want to, like, it's smart. You can like look ahead and see it. It's like a feeling. It's like, it's like a bat with sonar, and the current can like feel that like the change in potential essentially, which is the sonar coming from the resistor. And they're like, heck no, I'm going to try to, most of us are going to go through here, but some of the currents just like, it's like, well, I don't care if I have to work harder. I want to get out of here as fast as I can. And so they'll take the higher route and go through the higher resistance, even though they're spending more energy. They're just trying to get out of the thing, where everyone down here is just like, man, I don't care. I just don't want to I don't care if I spend a little more time in here. Less work I have to do. So, right, I have to get in a longer line, but it doesn't take as much work to wait in that line. I don't know. I'm trying to give you analogies because they really do set up here pretty well. But anyway, everyone good? Cool. And so what happens again? We don't get into the details here too much of it. I think Dr. Dungan explains it to you. I don't know if he really gets into the details of it neither. I think it's just, again, a concept he wants you to know, because we don't talk, this is the only chapter. There's one more chapter we talk about circuits, but it's not like this. We only talk about series circuits, and it's really, really easy, and it's really, really short. So this is all you have to know about circuits. That's why we're not getting into those details that you probably are interested in. But what happens is when the current splits, because it is making that decision, because most of the current would want to go through the resistor with less potential, with less resistance, essentially what's going to happen is that the amount of potential that's being spent for the total current, because it's going to come back together, is essentially going to be equal whether it's going through up here or up here. Again, there's ways to prove it. We're not in here to prove it. We're not here to be electricians or anything like that. And so what we just need to know is that for series circuits, the potential changes as it moves through series circuits. But as the current moves through parallel circuits, it just the potential, the change in potential is the same. So maybe that might be, but the change in potential is same. And this might be change in maybe potential changes might be better for up there, but the change in potential, this might be more appropriate for down here. Change in potential is same for all resistors in parallel. Okay, cool beans? So if I had, what I'm trying to say there, I'm not saying he's going to do this, but I want you to understand how extreme this goes, because sometimes this just helps students understand too, is that if I had 4 parallel resistors right here, and I had a current that came in here, right? It came in here and split 4 ways and then came out right this way, right? The change in potential for the total current that's moving through here would be, the total would be the same for all those resistors. It wouldn't matter like what their R's are. You still know that the change in potential there is going to be the same here for the current that moves here. The change of potential for the current that moves here is going to be the same. The change of the potential for the current here is going to be the same, and the change in potential is going to be the same for the current that moves through there. Okay, does that make sense? That's just a super extreme example. He's not going to give it to you, but I just want you to see how. And this could go on for a billion resistors. In fact, this is how your house is set up. And this is what he was trying to tell you about RMS values, okay? This is the, because trust me, I don't think he's going to test you so much on RMS values. Again, you can look at his questions to see what he's going to ask you, but you need to start getting that idea down is all. First, you just need to be introduced to it because we're going to talk about it more later on. But the bigger idea was that we need to set up our like RMS values are important because those are the values coming into our house. That's essentially, the RMS values of things are essentially the effective, yep, no problem, are essentially the effective values of things. Essentially, if we were to look at the AC currents and potentials as just DC currents and potentials, which are just the effectives. But everything in our house, right? If the circuits in our house were set up in series, that means that like the lights that we plug into some of our circuits won't light up as bright as some of the, or that we plug into some of our sockets won't light up as bright as some of the others, right? Because the potential will change if our circuits are in series in our house. But if all our circuits are in parallel, which is how they make buildings, all circuits in buildings, all circuits in houses, they're all set up in parallel. Every socket is in parallel with every other socket in your house. And that way, as the current comes through, the change in potential for all those sockets is going to be the same, which means that no matter what, everything that you plug into every resistor, they're going to be able to be supplied the same way, no matter, where that socket is in your house. That's how this stuff really, really expands out. Okay. So these are the concepts. Does that make sense? Now, to put these things together is really, really easy. Okay. You just add them, right? To get R equivalent for series, that's just R1 plus R2, right? For parallel, to get R, and remember R equivalent means the total resistance of that circuit. Okay. And so when you get this number, just make sure that you flip this answer, right? Because this gets you 1 over REQ. We need to be getting the REQ every time. This needs to be the answer every time. So you need to make sure that you're flipping this to get REQ. So, okay, cool. Everyone good with that? Okay, so did you want to, the examples can get kind of longer here. Did you want to go through one, or do you want to start the worksheets now? Because I can give an example of that. There's not, like, he doesn't have you do any of these things on the worksheet. He does on the slides, but he's giving you those answers, right? And please, if you have questions about it, send me an email, okay? I don't want to leave you hanging, okay? Like, if you need to know, let's talk about it. Please send me an email, okay? And we can discuss, how to put those circuits together if you need to. But also keep in mind, let me say this, rather than send me an email, come to SI on Monday, okay? Because which is tomorrow. And I will do a circuit question. I'll do a circuit question in there, and then I'll show you how to do it then, okay? To work through an example, okay? So all right, so let's get going here. What do you mean 7 circuit questions? Oh, I'm sure there are. Like it's a whole chapter, Levi. So there's gonna be. He's not even finished with the chapter. Wait till he's done with the chapter. You're gonna be like, man, there's all kinds of clicker questions for circuits. So that's just to the point we've got to now, right? So just keep that in mind, my friend. There's more to come, but you also have the answers to those, right? The answers, the worksheet questions. He doesn't have you do any of that stuff. He doesn't have you put any resistors together in series or parallel on the worksheets. Okay, so that's what I'm saying. Like, and if he wants you to, you know, do that, he gave you the key for that. He also posts the lecture so you can listen to him re-explain it, and you can look at the work as he does it. Right, that's the point of him posting the lecture, so you can watch it as many times as you need to. Look at the work, write it down as he's doing it. Okay, all the answers are on there. You can slow it down, you can pause it, anything that you need to. Right, he walks you through those questions. But again, I'm willing to do it too. Just we got to get going. All right, and I'll do it tomorrow. Well, during SI. So, okay. So I think the first is everyone like for election. Let's just start. I want to just start with the first worksheet and just try to get as far as we can. Okay. And so is everyone cool with the first? I mean, we can do them, but I think everyone's okay with like bringing charges together and stuff, right? And there's a ton of questions here. I hate to spend time on the simple ones because he spent 3 weeks on that stuff. And it's, as you can see, it's not really the focus of things, but I think you all know how to answer 1 and 2. Okay. If you don't, send me an email and I'll explain them to you, but they're really, really straightforward. We need to look at these other really harder questions. Okay. So, well, if we have time, we'll come back to it because they're really not that hard. And I'm telling you, we're not, based off the time, there's some really hard questions here. Okay, so let's try to get through those really harder ones because you're going to see. I mean, 2's going to be not as important in the long run when we look at some of these other questions. But I don't want to ignore it. So let's get through some of the hard. All I'm saying is let's get through some of the harder ones. Then we'll come back. Okay, sound good? I don't want to ignore it, but I kind of want to do the harder ones first. Okay. And that one's a little bit more straightforward. So number 3, right? That one is really yes. Worksheet number 1. It's called electric charge, force, and field. Okay. And so number 3 is can everyone see does everyone have the worksheets in front of them? Because I don't have them to like post and this is, it's only going to help if you're able to see. I mean, I'm going to try to draw them, but some of these things you're just going to have to be looking at the worksheet. Okay, so make sure you're looking at that thing. I'll try to do my best to draw, but I'm no machine. This thing's done for us, right? Okay, so it says assign the correct charge on the metallic spheres so that the shown forces make sense. If the spheres can't be assigned charges, explain why. So what is going on there? Who can tell me? Again, I'll explain it to you, but I think some of you may know the answer here. Are both those pictures? Let me ask you in this way, rather than looking at them individually. Are both those pictures correct, or is one of them wrong and one of them correct? Yeah, have a good one, my friend. Okay, so what's wrong with them? Good. So he has this, and then he has, again, I'm not a machine. Oops, there's some charges there. What am I doing? And he has this, right? So these are all the same. These are all the same size. Okay, where this one is much longer than this one. And so, and he says assign charges to these things, right? So why is the top one incorrect? Why is this one, the top one, wrong and the bottom one correct? why can we assign charge? I mean, it's up to you, just as long as like this is positive and these two are opposite, or if you did negative up here and these two positive, that's still correct. Because you can really do what you want to here. But just as long as these two are the same and the top one's opposite, we can definitely do that. But why can't we assign charges to the top? Good. Newton's third law. Okay. Remember, this force is equal and opposite between the individual charges themselves, right? And so, and that's what we see in the second picture is all those vectors are the same size, and they're either pointed towards each other or away from each other, indicating either attraction or repulsion, right? But here, this one is much larger than this one. Not good, because if I just have two charges there, these should be the same magnitude, same size. And how do we know that? Because of this equation, right? This would be Q1, this would be Q2, okay? And so it doesn't matter, right? Q1 and Q2, this force is gonna be the same. So one can't be larger than the other. That's a big no-no. Okay, but down here, because it's saying these forces are equal and opposite, correct. These forces are equal and opposite, correct. These forces are equal and opposite, correct. That's why that's right. Does that make sense? Because those should all, from the individual charges themselves, they should be. Okay, so that's how that's solved. So second one, you can assign charges. The first one, you can't, okay? Good? All right, and I'm definitely gonna have to start recycling so so the next one says that you have these charges and he says shown spheres are at the vortices of the right triangle as shown, shortest sides 3 units long, longest side 5 units long, right? So he's trying to say this is 3, so that should be a little bit closer. He's trying to say this is 5. Okay. And I don't know if we use those necessarily in here, but he wants us to know that. And then the larger sphere has 4 E charge. So I drew that arrow. Let's just call this Q1. It has 4 E, which means like 4 times the charge of an electron, right? And the smaller spheres have charge E, which is just the charge of an electron. And so he says, draw forces on the lower right sphere due to the other 2 spheres. Draw a longer arrow for larger force. Draw net force vector arrow. Also draw the components of the net force is vertical component up or down. Okay, so draw forces. So how should I draw it? Who are the forces going to be equal for both of these? Is the size going to be the same, or is it going to be and these are repulsion, so I was drawing the wrong way. But are they going to be the same size, or are they going to be is one going to be larger than the other? Why aren't they equal? Which one's larger? It's both, right? Like this one's not only closer, but the charges are also larger, right? It's like it's both, right? It's both versus like this one right, it's further away and the charges are smaller. So yeah, so this should definitely, good job. This should, I mean, I don't know how much longer you want to make that extreme, but like that's one. And I mean, you definitely want to make sure you show it, right? I mean, this is for your understanding, right? You don't turn these in. So how large you make that is, show it. Say like, no, it's this much larger. And you could calculate, he gives you those numbers to calculate it, right? But anyway, all right. So now he says, draw the net force vector and the components of the net force. So how's that gonna end up here? How do we get the net vector?
By rearranging them to just add the vectors.
Okay, good. So you're telling me tip to tail is what you're telling me, right, my man? And I think everyone else is also saying that as well. Yeah, awesome. And again, does it matter if I do the green one first and then put the tip of the blue one on the green one, or if I do the blue one first and then put good, because it's adding, right? It's adding. So I'm just going to do that for a second to do the tip to tail, right? Then we draw from the tail of this to the tip of this. Right? And so that's what we have. Man, I have a bump there. You guys can see that clear enough. I think that's pretty clear. So there we go, right? Just keep in mind that this, right? Because this force is on the charge, but we just moved it over here to do the tip to tail. Okay. And then he says, okay, everyone okay with that answer?
Yeah.
Okay. And then he says, what is the vertical component? Well, he wants all components to that thing, right? So whoa. Let me do this. This will be easier. So I have this like X and Y. Okay. So now he wants components of this thing. So how should we do the components? Who can tell me? It really doesn't matter what angle. So, if we just want to make sure that we pick an angle too.
You pick a angle theta relating that net vector line with that horizontal line, and you use sine and cosine and get the components.
Good. So did you say that one?
Yeah.
Okay. It doesn't matter. You can do this one too, because the answer doesn't matter, right? Let's do it for both. Let's just do it for both, but let's move fast because he doesn't ask you to do this. Okay, so remember, it's just enclosing the angle. So for this one, right, if I wanted to enclose the blue angle, right, I would move to the right first, and then I would move down, right? If I wanted to enclose the green angle, I would move down first, and then to the right. Okay, so it doesn't matter, whichever one you choose, okay? And so which direction is the vertical component pointing? Up or down? Okay, so there's our answer. Good. So we could, so now number 5. That's that answer. Okay, so number 5. Well, I'm gonna try not to erase too much stuff. I'm gonna eventually have to. So an electron is orbiting clockwise around a proton. So we have this that's just like, it's in the center, right? And then there's this electron, it's moving around it, right? And so it says clockwise. I did counterclockwise. And watch me on my details, because one thing I noticed here this week is like I must have an older version of the worksheets because some of my stuff is like in a different order than what you guys have. So he must have changed some things to make them make more sense, which is great. But some of my things are worded a little bit different. So if I say something different or something looks weird, please point it out so I can adjust to what you have. But I think this is what everyone says. So is orbiting clockwise around a proton and a hydrogen atom. Okay, sketch proton, electron in the orbit. There. That's what we have. And then what is the direction of net electric force and field on the electron? So which way? So this is what type of motion is this? Who can tell me? Good, it's circular motion. And so that means we always have a force towards the center of motion. So even if you didn't know where to put the force, you could literally go back to that concept and it tells you the answer, right? You could go, oh, this thing's I don't know. I mean, I'm assuming this would be the electric, if you didn't know what's going on, right? I'm assuming this is electric force, but I know that this is definitely there. There's a force towards the center of motion, right? But we know that the force is that way because we know it's attractive. But what's the so those are the two reasons why we know the direction of the electric force there, right? But what's the other reason? There's another like more important reason. Remember, it goes back to this very important thing right here. Okay. Good. It's the field, right? Because does that force exist without a field? Does that electric force exist without a field? Remember, no, that's what this is trying to tell you, right? That's what this is trying to tell you. That field's always there. You have a charge in that field, though, there's going to be some electric force going on, right? And then, yeah, that thing, right, that electric field has some sort of potential, and that electric force is going to have some sort of potential energy associated with it, right? That force is going to do some work on the charge in that field. Cool. So makes sense? Everyone good there? I mean, if you wanted to make this even more appropriate, you could definitely add. I mean, we're not asked. I don't think. Yeah, he doesn't ask you for it, but I would love to see that from you all. So there we go. Number 6, you're holding a 0.5 kilogram cart and containing a charge. It's positive away from another. It looks like this is like some like charge that's like nailed down. It can't move. It's just kind of like it's really heavy and big, and it's just gonna sit there. It can't move. It won't be this, but this thing, because it's on wheels and stuff like that, it's able to move. That's what he wants you to think here. So when is the acceleration? Oh, sorry, not when. What is the acceleration of the cart at the moment you release it? So you're holding it right now, right? That's what the very beginning said. He said neglect friction, and then will the acceleration increase, decrease when it's moving away from the charge? Will velocity increase, decrease? Why? Okay, so let's start with the beginning. So at first we're holding it, right? So at first I have to push it. Why do I have to push it this way? Why do I have to apply a push that way? Because what? Why? Because of the electric force, right? There's an electric force this way, right? And so if I'm holding it still, that's equal. He's not really asking us this, but I want you to hear it. So that's equilibrium, okay? We're at rest. So those are equal and opposite, okay? And then what happens? This goes away. Bam. So what does that mean? Just from the picture, we have what to the left? Let's call that positive x.
Acceleration.
Not almost, my friend. I mean, I do want that answer, but remember, there's something we got to say something first. Oh, you guys are actually saying a lot of really good stuff now. But acceleration, remember, acceleration is always like the last. We want to say it. It's super important, but it's always going to be there because we have a what. That's the word I was kind of looking for out of everyone. I'm getting a lot of good things in the chat, but that wasn't, and I'm going to write all those things down. Net force. That's what I wanted. That was the answer I was looking for. But then everything you all are saying is correct, and we're going to write it all down. But remember, it needs to be in your head because that's how we talk about in physics, right? So I was pushing it. When that push goes away, the electric force turns into the net force. And when there's a net force, what does that mean? That means that the thing's gonna well, if it was at rest, it means it's gonna speed up in the direction of that net force, right? And so that's what these two things indicate. And remember, the acceleration is just the measure of the net force. It's just measuring how much the net force is affecting the object. Okay, that's why we always want to talk about net force first, because it's net force that's making the object speed up. The acceleration is just measuring how much the net force is affecting that object. Okay. And then you know what? He doesn't ask you for it, but I'm going to write it because you all are just so amazing. You said electric fields there, and you're right. I should have probably asked you. He doesn't ask you for this, but I should probably ask you for that, right? Because this helps put a lot of things in perspective. Like there's an electric field coming from that charge. So look at that. It's literally confirming this concept we're talking about over here about the force, right? A positive charge is going to move, right? Away, right? It's going to move in the direction of the electric field. Sorry, I was almost going to say that wrong. It moves in the direction of the electric field, right? And that's exactly what this card is doing, right? So a lot of things to see here, okay? And then will acceleration? Wait a minute, I'm skipping something. Okay, yeah. What is the acceleration of the cart the moment you release it? So he's asking us to now do what? Write a what based off our what?
An equation based off the free body diagram.
Perfect. And I think now, please tell me if we got to talk about it. Don't be bashful, okay? But I think we all know that it's right. I think this is a second law is being applied here, right? Like that's kind of drilled into our heads from last. But if it's not, please say so. I'm just saying, like I remember being sick. Oh man, here we go again. But it's a good thing because it's showing you it never goes away, and there's only one way to do this, right? So we know Newton's second law is going to be applied here because there's a net force being applied to the cart, and that's the object of interest here. Okay, now we chose to the left as positive, which is what I would always suggest. Try to choose that direction of motion positive, since we're able to be liberal about it and choose it. And then right, and then we know that this is just trying to state Newton's law in terms of an equation, right? And then we fill in this side of the equation from our free body diagram. Well, all we have is the electric force there, which we know is this equation, right? We talked about this, right? That's the only force there. It's clear from the picture that's the only force there. So then that means, right, we can pop that in here, right? And we could put this as mass of the cart. I mean, it's always good to try to be, especially this semester, like try to be as specific as we can with these things. So we know, exactly, but this is gonna like you can't. He's not asking you for a number here because it actually takes some calculus, right? Because this is like delta, like this R is like changing, right? It increases as it moves farther and farther out. So it's kind of hard to do too much with this, but you can do it like at the moment because I think he gives you. Maybe not. I don't know. But this is how it's done because I don't think. Yeah, I'm not seeing the distance in there unless I'm missing something. Oh, it is. I was missing it in there. The distance is in there. Yeah, thank you. That's why I was like, man, am I missing? I could have swore that's why I started changing what I was saying because I'm not seeing it. Okay, so that is 1 meter. So you do have this R. So sorry about that. Apologize about that. So otherwise we would need calculus. So this R is going to be 1, right? Because he's asking about just at that moment. So first we want to solve this for acceleration. Sorry about all that. I started looking at the givens and I was like, wait a minute, do we know that R? And we do. And this is the mass of the card, which he gives to us, which is 0.0 kilogram. And then, and this is equal to acceleration. So you can actually get a number here, right? He gives you everything to get a number here. You can actually get a number here. R would be 1, M would be the mass of, say, you guys all know how to do all that. Okay. So that would be your value for acceleration. Now, would it increase or decrease as the cart moves away from the charge? Is the acceleration, and keep in mind, when he's asking you that question, he's actually asking you about net force. Even though he's saying, is the acceleration going to increase or decrease? He's actually saying, hey, is the acceleration going to increase or decrease? Yeah, I don't have a number calculated. That would be nice though. If anyone else, I believe it's 36 though. That sounds right from grading a few papers. So I think you're good there. Sorry about that. Sorry, I should have got a number. My bad. Yeah, that's 36. Okay, cool beans. Great job, everyone. Okay, so now remember, you can, if you want to look at this in terms of acceleration, fine, that's fine. But remember, you can't talk about acceleration without net force. And so he's essentially just asking you about we know the electric force is the force here, and not just the force, but the net force. So he's asking you, as you get further away from this, as this positive charge gets further away from this positive charge, is the electric force, which is the net force, increase or decreasing? Decreasing. So that means that if the net force decreases, automatically the acceleration that's going to always go along with that net force will also be decreasing, right? Yeah. I mean, absolutely. I mean, you could definitely look at that equation, say that R squared is totally determining that. Absolutely. And so what does that mean about acceleration decreasing? Is it going to speed up or slow down? So remember, remember, we would have to say the net force changed direction for this to slow down. We would have to say that. When we say that it decreases, we're saying that it's like going from like, I don't know, 10 newtons to 5 newtons. But it's still in this direction and it still has a value. It's just not going to speed up as fast, right? Speed up because it's decreasing. Right. Well, remember, think net force, but you're right. Why is acceleration still in the same direction? Because net force is still in the same direction, right? But you're saying good things. I'm not saying what you're saying is wrong, but we got the thing about, and this is why acceleration still can be kind of abstract sometimes, because you can't forget that it's directly connected to net force. Like it doesn't even exist. Remember our saying from last semester, net force is the source of acceleration. So it's always good, even if you're asked about acceleration, it's always good to start talking about the net force first. And then everything that you said about the net force, that's true about acceleration. Okay. But acceleration is just the rate. Remember, it's like when if I say a car speeds up from rest from a stoplight, that's just changes in velocity. If I say a car speeds up very quickly from a stoplight, that's acceleration. Acceleration is a little bit different. Okay. When we're actually talking about it directly. This rate of velocity. Okay, so it's gonna, because the net force, this is why that's important, because the net force is still in the same direction as displacement. See, the only thing that would change about this picture is just like that vector would get smaller. But everything is still in the same, net force is still in the same direction as the way we're moving. So that means we got to still be slowing down. It's just the value went down. Again, we would have to say that it changed direction for you to slow down. Acceleration, the net force, right? All of a sudden that electric force would have to change direction and then you would start slowing down. But if it stays in the same direction, which it's going to, right? Why wouldn't it stay in the same direction? Those positive charges are always going to be repelling each other, right? Then it's going to, just go, it's just going to get smaller and smaller, but it's still going to continue to speed up. Again, this is more of a question from physics 1 than physics 2, but does everyone understand? If not, please ask questions. The point of this is so that you understand. So if you need more, right, please say. Okay, so let's move on to the next. We're moving pretty good. We might make it 12 these. I'll be honest with you. Okay, so but we got to stay at the same pace. So but please ask questions, okay? Please don't. No, it's speeding up the velocity. It's really, really bad to say increasing velocity, decreasing velocity. It's not that it's not incorrect. Listen to my words. It's bad because as a physics student, those words don't mean enough to us yet. And so when we say velocity increasing or decreasing, we still have to make another jump to say, oh, that means speeding up or slowing down. So it's better, instead of saying velocity increasing, decreasing, changes in velocity, to actually use the word speeding up, slowing down, because that's making a very firm statement that you and I both understand. Someone who's never taken physics would understand. Cool beans? Right. It's as if it's speeding up or slowing down, but it has to be continually speeding up because net force is in the same direction. Net force doesn't change direction. It decreases. It doesn't change direction. Right? There's a difference between decrease and change direction. Does that make sense?
Yeah.
Okay. Well, there's just a student here that has a question, and I just want to make sure they're okay.
Yes.
Okay, because it's more physics 1, okay? And please, if you still want to dive deeper into that, send me an email. Let's dive deeper before the test because you need to know it. Okay, but let's answer these worksheet questions. Okay. Negative electric potential question, worksheet. A negative charge Q is fired through a small hole in the negative plate as shown in the sketch. The oppositely charged metallic plates have charge Q in area A. Draw the label and the direction of electric force and field on the charge Q, and it's moving between the opposite charge plates. Is the charge speeding up, slowing down? Neither. As it moves towards a positive plate, use concepts of force and charge to explain this. So please, now this is your chance. Those of you already know this. Some of you already know this. Some of you, this is your chance to use it. And you'll see how helpful this thing is going to be for you and why you should memorize it so that you can write it. The minute that you start that test, you can look at your scratch paper. You'll write this picture down on your scratch paper and you'll use it so much to answer questions, okay? You can't bring this into the test, but you can memorize it and write it down. Okay? I mean, that's a way around. That's a loophole, but there's nothing wrong with there. You can do that for any test, right? If you can memorize things, and then I would do that a lot. I would memorize things, right? Like things like this. I don't know if you guys do this. I did this all the time. Like this is what got me through biochem. I would make pictures like this. And then what I would do is the minute I got my test, I would draw all my pictures that I had that I had made for that test. And then I would start the test and I would have all these things to refer to, right? Even I couldn't bring in any note, but there was nothing wrong. She'd even see the pictures and go, oh, what? How cool. Because there's nothing wrong with that. Like, you can do that. It's like, so anyway, let's move forward. Okay. So let's use these to answer this question because it answers all the questions on this whole worksheet, this picture. Okay. So again, I mean, I think we can all see the picture, but I'll and one thing he wants you to know is that this hole is like so tiny that like essentially the areas are the same on both sides. Like that's what he's trying to tell you. in the question. So this thing, it gets shot in here, right? And so it's going to be moving this way in the electric field. Now, first of all, just tell, like, yeah, I'm sure the question asked. There's no way the question doesn't ask, but we shouldn't wait for the question to ask. What should we draw immediately? Kind of like our free body diagrams, right? But now the free body diagram is going to kind of include fields. We should be able to just draw them automatically, right? Exactly. Look at you all go. Like like don't worry, don't wait for the question to ask. Just be like, okay, this is my situation. Then you know what? Like I'll come back to the question here in 2 seconds, okay? But let me write this. And who knows, you may have answered the entire question just by writing all the oops, I drew that wrong. Sorry, I got too excited. You guys are so awesome. Okay. Exactly. Yes, that's right. It's the concept that we can check ourselves, right? It's like, oh man, that's on the concept. Electric field should always be opposite direction of the negative charge, right? Which is what does someone have a question? Okay. That's what this is telling us, right? We're essentially using this part of the picture, right? Where we're looking at this negative charge, and we see, like, the negative charge, it moves in the opposite direction of the electric field, right? That's a concept that we see from this picture. Okay, but this is the things we already know. I keep hearing someone. Okay. For some reason, I keep hearing someone trying to ask a question, but maybe it's just me. Okay. So we just did the first part, right? Draw and label electric force and field. There you go. So we just did that between the plates. And then he says, is the charge speeding up, slowing down? You can't hear me? Uh-oh. Someone said I can't hear anything. Okay. Sorry. Okay, good. How do we know it's speeding up?
Is it because the net force, which means the acceleration and the velocity, are in the same direction?
Oh my goodness. That was awesome. I'm going to erase this. I wasn't expecting. That was amazing. The net force is in the same direction as the way we're moving. So that means that we have to, oh my goodness, that means we have to be speeding up. Did everyone get that? Yeah, ball rolling down the hill. We're going to have to talk about kinetic energy here in a second, but I love this explanation. I don't think he does say use force. This is beautiful. This is what he wants you to say first. We'll get to the energy thing. I love what you're saying, but he's actually saying, no, tell me about force first. And what you should be saying is based off the last question we did, right? You need to say to yourself, force, if force and displacement, or net force and displacement are in the same direction, this thing's speeding up, right? And so that's the way that's the force concept. He says use concept of force to explain. So does everyone understand that? Great. So then C says write down equation of potential energy. Now, again, I want you to use that picture here, okay? I know what he's saying here, but let's jump to that picture that we're going to use on our test, right? Write down an equation of potential energy of the charge when it is some distance d from the negative plate. Is the potential energy positive or negative? Now explain why the charge is either speeding up, slowing down, or neither, using the concept of potential energy. So first of all, before we do any of that, let's just answer the question. Okay, and this is going to like I said, there were some concepts we didn't talk about, but we're able to talk about them now with these questions. Okay, so he says he wants us to write down the question. Before we do that, what is, as this plate using this, remember we're using, it's a negative charge, we're using this side. As this negative charge moves closer and closer to the positive side, is its potential energy increasing or decreasing? Good. Going from high to low. What is the sign? Now, this is a concept. You don't, right? This is a concept. What is the sign that we can give either potential energy or kinetic energy that indicates a, oh, wait. I got increasing. Are you, does it make sense why it's decreasing, Quinn? Like we're going from a high potential energy to a low, right? Kind of like uphill to downhill. No, it's okay. I just want to make sure you're good. But you're cool beans with that? Awesome. Okay. So yeah, so thank you. Yes, thank you. Yes, so we know this is a total concept here. Where was I answering this question? Here. So this is a total concept that make a mess there. That we need to know. So we know that like decrease in energy is always in, oh, my pinch off, is always indicated by a negative sign. And increases, and this is like work. If work is negative, that means decrease, positive, decrease. I mean, you can say that. We talk about that a little bit different in terms of energy coming in and out because we want you to understand the concept, but it still means the same thing. But especially for potential energy and kinetic energy, you don't have to, like, when he's asking you for the sign, you know, the minute you say decreasing, you know the sign for the thing. The minute that you say increase, so if I say kinetic energy is increasing, it needs to have a positive sign, or essentially it would be like the change would be positive here, right? It's really the change we're talking about, right? And so the change in potential energy, right? If it's increasing, it'll be positive. If it's decreasing, it'll be negative. If kinetic energy is increasing, it's going to be positive. If kinetic energy is decreasing, it's going to be negative. Like that's what that means, right? And that's exactly why this equation is always written this way, because this negative side, there's an unsaid positive out here. So all this is saying is that as the potential energy increases, as the kinetic energy increases, the potential energy is going to decrease. That's what that negative sign means here. And that's all that's trying to say here. And then that's how that carries over into here, like in terms of the concept. And then that's how it carries over into answering this question. Okay, now we're going to still write an equation, okay, because he wants us to do that. But do you see how we were able to answer this question with just like concepts? Like, right? We knew this. We knew that a positive sign for energy means increase. We knew a negative sign for energy means decrease. We were able to look at this picture and we said, hey, for this negative charge, the potential energy is decreasing. So that means that the sign has to be negative. Has to be negative. Everyone cool beans with that? Cool. And then he wants us to write down so actually that would be the wrong one. Make sure I'm saying some of these equations. I wonder, actually, there's actually a few equations we could use here, but same from the negative plate when that means. Oh, is that what it says? Uh-oh, do I have something written? So I might have some, this might be where I have something written. Oh, I see. I see what you're saying. You're talking about, oh, okay. It says write down the equation for potential energy of the charge when it is some distance away from the negative plate. It's still decreasing as it moves away from the negative plate though, right? because oops, that's what this concept's saying, right? As we no, I'm glad you asked the question. As we move away from that negative, right, we're decreasing, right? So whether we look in relation to this or that, we could say, is the potential increasing or decreasing in terms of the positive plate? It's decreasing. But if we said, is the potential energy increasing or decreasing in terms of the negative plate, it's still decreasing. You see what I'm saying? It doesn't matter for this chart. It doesn't matter which side, but I'm glad you asked that question. But I did want to make sure that I was answering it, because I'm getting some of these. I've noticed I get some orders wrong in SI, and I didn't realize it until I saw some of the worksheets you guys gave me. And I was like, oh man, I don't have that same order. So I'm answering the question different than what you guys have. So I'm gonna get confused. I don't want that. All right. Okay, cool. So I think that's it. And then what would be the so he asked for the equation. What equation would we write? Sorry about that. I should move over here. What equation do we need to write for this? And it's for you. So he's asking actually an interesting question. He's not asking for a change in potential energy. He's just saying, like, tell me the potential energy, like, right, like at this particular R. You see what I'm saying? So that would mean that that's where that's why this equation is the valid one here. Oops. And one of the charges would be the charge from the plate, right? And then this would be the charge, the negative charge in there. There we go. Does that make sense? He's just wanting to know for a specific spot. If he asked you the change in potential energy, that's a different equation. That wouldn't be this one. You couldn't even use it. You would have to actually use this one if you needed the change. Cool beans? But he's not asking you for the change, right? He's asking you for this. Cool? Please let me know if you don't understand, because this is where we give you so many equations for the same value. That's why it's confusing. So please ask. Like, I understand that's where confusion can be. So the negative value we are assigned. Yeah. So. Okay, so yeah, I forgot you guys do that in here. We're not allowed to do that in the. No, you're saying good things. We're just not allowed to do that in the Cal base. It's a cheat. It works every time, but yes. So what you could, Dr. Dugana wants you doing this. Good way to bring that up. So you use the charge in here, right? You can actually use the signs of the charge in this equation, and so since one of them's negative and one of them's positive, that means that this is going to be negative. Does that make sense? He wants you using that trick. Just use it. Use it. Okay? Because the only other way to get the sign for the potential energy is looking at the work, and not that you couldn't do it, but this is just way easier. So does that make sense? Cool. Yeah, I mean, I suppose, because if you do the no, I haven't. I mean, if you do the negative, I mean, it's you can't, like I said, that sign thing's a trick. So yeah, it's always good to look at, like, because this thing, the particle's moving because it's being, like, attracted to the positive charge, right? So that's why, again, this is a trick. This is not the actual way to get this sign. This is why it might be confusing. So don't worry. But yes, I would say always use like, if you have this situation, like whatever's causing the pull, the pull or the push, using this. Let me say it like that. Does that make sense when I say it like that? Okay, sweet. There we go. Okay. Explain why the charge is speeding. Okay, so do we understand why it's speeding up? So it's we said it was speeding up. We already answered this question, but do we understand why it was off of this? So we said, right? But he's asking, like, we explained it in terms of force. Can you explain in terms of energy? Exactly, right? And we see, right, we know kinetic energy is 1/2 mv squared. So we're saying that the v, right, essentially we're essentially looking at, like, it's delta v, right? And so yeah, so like this is what that's like the cause of the change in the kinetic energy. So yeah, and the velocity is increasing in this case. That's why if velocity was decreasing, then the change in potential energy would be positive, and the change in kinetic energy would be negative. Okay, that's how you know. Okay, but since the change in potential energy was negative, we know the change in kinetic energy is going to be positive, so therefore the velocity is increasing. Do you see how you get to that logic? You have to say all that. Not to him. As a student, you should be saying all those things because that's how you understand it. Maybe I should say it like that. I mean, he may ask you. I mean, it's part of this question, but to say it like a poem is really good. Everyone cool beans? Okay. I wasn't hearing from anyone. Just want to make sure. Okay. So we've answered D already then, right? We talked about C. D we just answered because he says, how does the change in potential energy related to the kinetic energy? Answered that. Is the electric field in between the plates same or different? So now that question, is the electric field in between these two plates, is it constant? Is it changing? Let me kind of clear some things up here. So the electric field is constant, is it changing? This is actually a concept here. It's not like you can calculate it, but it's a concept. Oh, yeah, Jenna. That's exact that. No. You're thinking right, is what you're thinking. Because remember, that hole's so tiny. It's essentially he tells you in the question essentially the plates, the areas of these plates are identical. So the minute you hear those words, area is the same, charge is the same, because that's exactly what he says in here. That's when you know it's uniform. Absolutely. And when it's uniform, again, I just want to make sure we understand. There's a change in potential. Okay, there's a change in potential, but the electric field stays the same value no matter, right? It does. The change in potential is just indicative of an electric field being there, right? We can find out if it's changing or not as well, but that's how you as students right now just need to see it, and you don't need to see it any deeper. Don't worry about it saying, oh, well, do I have to be able to tell by the change in potential if the electric field's changing or not? No. You should be able to tell if it's changing because of other reasons. You don't worry about using the change in potential, but the change in potential always tells us that there's an electric field there. And actually, if the electric field's constant, and this is a question coming up here in 2 seconds, that means that the I'm just making up some numbers here. Okay, so like as the some of you, this might really look familiar, right? As we move through here, the potential changes very consistently. There's the same that when you see this situation, or when you know the electric field's constant, when you know the electric, well, that means the same when you see the situation. When you know the electric field's constant, you know that the change in potential energy is constant. Change in potential. So sorry. Change in potential. I don't want to botch this. It's really so easy. These words are so similar. Okay, so they're going to be equally spaced from each other until you get really far away. Like if this was really far away, like as it got closer, like the drop to zero would kind of be a little larger increase, but it would still be in increments like this. You'll see what I'm saying here in a second. He asks you a question like this, and then you'll totally see exactly what I'm talking about. But does this make sense what I'm saying right now? Essentially, each one of these are an equipotential surface. Okay, so there's a change in potential between each one of these, and it's the same. The change in between each one of these is the same amount. The change is the same, right? Because the difference between the spacing is the same, and it's just a difference of, like in this case, 10 every time. I don't know if it's going to be 10 every time, but it's changes 10 every time. Right? Some of you, I know you know where I'm leading to with this on the worksheet questions, but anyway, this is really important. It's going to be important in the future. So so he asks, is the electric field between the plates same or different? It's the same. It's constant. It's not changing. The electric field at every point is the same value as you move through here. Okay, so if it's 10, if it's 10 Newton meters right here, then it's also 10 Newton meters right here, 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 10 Newton meters right here. Does that okay? It's the change in potential. It's the potential that's changing, and that will stay. The change, if the electric field's constant, will be constant. The change will be constant. Cool beans? Cool. And so, how do we know it's constant? What's the equation that we use to prove that? So we just said a bunch of concepts which need to be in your head, and you need to make sure those are memorized. But what's the equation that tells us that it's constant? So that one works, but we can. So he actually, if you look at his slides, he gives you two. But I think like he's cool with you using that one, and that's probably the one he's going to use on the test. But please beware, this isn't just me. He gives you two equations on the slides. Okay, so I think it's based off of what he's saying. All right, so this is, we hadn't talked about it yet, and again, I don't have time to go into too much detail because I want to get through these worksheets, make sure you guys have the answers to these worksheets. But if you need detail, again, there's SI tomorrow, or you can send me an email, because you should know the details on this. Okay, I just don't have time right now. But Gauss's law, okay, don't forget about flux. Don't forget about Gauss. Remember, Gauss's law is actually how we always calculate the electric field in physics. It's just we gave you a few equations to show you, some generalities. But Gauss's law is how we always calculate. It doesn't matter if there's one plate, two plates, one charge, 10 charges. What we do is Gauss's law lets us use the density of those charges, the charge density, and allows us to calculate them. Because when you start having a ton of charges on a plate, or a ton of charges just in a specific area, to count all those things up into atoms is a pain in the butt. And so Gauss's law lets us use charge density. Okay. And so what we know is that when we put flux together and use Gauss's law, because flux is really Gauss's law, use Gauss's law to solve for the electric field. So this is really Gauss's law right here. We see that the electric field, right, is definitely, this is, and I think he's making this big Q, and that's fine. It doesn't matter. Big Q. Is definitely can be equal to this. This is correct. Like, this does describe the electric field here, and I think he tells you on the slide that this is good. But literally right next to this equation, he says, actually in physics, and he's right, we would actually write this way. And the reason why is because, like I said, we want to describe this in terms of charge density. This sigma right here is surface charge density. So sigma lambda's linear charge density, but surface charge density, right, is just how much charge per area. And so that's why we end up canceling here, because when I solve this for sigma, or I'm sorry, not sigma, Q. When I solve this for charge, it's sigma times A. So this would be sigma times A up here. The areas cancel. And so now this equation becomes this one, right? So that's how we get there. All right. But actually both, he tells you on, and he's right. I mean, there's nothing wrong with what he's saying. He gives you both of these. So I guess know them both, be aware of them both, and he could either ask you for this one or this one. But this one is, I would say, the more appropriate. Let me say it this one. If you know Q, then you would want to use this one. If you know surface charge density, then you'd want to use this one. Okay, that's really how you determine which one you want to use, I'll be honest with you. And then, yeah, there's also a lambda that he gave you, which is, again, part of Gauss's law. It works the same exact way. So you start with this equation, and then and he doesn't go through too much of the math here with you, but lambda is linear charge density. Okay, and that's equal to how much charge per length. And so just like we you would solve this for Q, which is equal to lambda times L, and then I'm completely out of space, but you saw what I did over here. You would do the same thing, pop that into there. You have a new equation. So so the area has distance in it, right? The area. So remember, for Gauss's law, the area is the area of our Gaussian surface, and the radius in there is going to work as our distance. And then what ends up happening here is that based off, because we would give you this number, surface charge density, and so based off how much charge density per area is on this plate, we can also just use that to calculate the electric field in here. Only if it's constant, right? Only if it's these two plates. It doesn't work like that if it's not these two plates. Okay, keep that in mind. I think that's where you're going. You're thinking, wait a minute, like, this is only true. The things that I'm writing over here for this lambda, for this sigma over here, are only true for this situation, for two oppositely charged plates. Because keep in mind, like, things can get really complicated here. I could have a charged plate, right? And then I could have that opposite of just a wire, right? So the electric field, right, this is going to look really weird because it's going to be enclosing on this wire, this like thing with length, right? The electric field is going to be like, it's not going to be constant in here, because the values of these two things in the areas are going to make this thing there's not going to be these, like, maybe right in the center there might be a few straight lines, but most of them are going to be curving, right, to try to enclose in on that line, because this has so much area and that wire doesn't have any area, it just has length. So when I put these two charged surfaces opposite of each other, right, the electric field is going to look a lot different than if I have two charged plates. Like, if I have two charged plates, the electric field's very, very evenly distributed between these two plates because of their areas, right? But the minute I change, like, the shape, like if I turn that to a wire, or turn that to a sphere or something, then this idea changes. Does that make sense? And that's where we would need a Gauss's. We would need an electric field equation for this side. And then like remember, if this isn't a plate, if this is like a wire, then we couldn't use just one equation. We would have to then develop an electric field equation for the wire too, and then we would have to add them. Add these two equations. At any point within this electric field to like figure it out. But if it's not two charged plates, then it's the difference of two equations. But if it's two plates, then the field's constant between them. It has to do with the plates have to be. Oops. Does that make sense what I'm saying? How the distribution depends on the objects themselves, which is what Gauss's law is trying to say to you. That's why we come up with those Gaussian surfaces, because we got to look at the object itself, right? The shape of the object itself becomes very important in terms of how the electric field is going to look between, a plate and a sphere, a plate and a wire, or two plates, two spheres, two wires. Does that make sense? Cool. And again, like two wires, that'd be pretty consistent too. Like, if I have two charged wires, the electric field, there's just it would just be in this one dimensional area, but the electric field would be constant there, right? Because these things don't have these things only have length. They only have one dimension, right? They only have meters. So the electric field would only be one dimensional here. But it would be constant between those two wires. We're going to talk about that situation actually after this test, because this stuff doesn't go away at all, even when we introduce magnets. So, but anyway, does everyone understand the answers to this question? Cool beans. If you have questions, please tell me, okay? Oh, yeah. Thank you. Got too excited. Okay, if the electric potential, not potential energy, but again, so this is this answer. So remember, all these answers are coming from this. Do you see how valuable this thing's going to be to you on the test? It's not going to answer every question, but it's going to help you a lot, so much. Is the potential, not the potential energy of the charge changing when it moves towards the positive plate. Again, we're looking at this picture over here, this one. We're looking at the negative side over here, right? So as this thing moves from the negative side to the positive side, is the potential, look down here, this is the answer, it's right down here, is the potential increasing or decreasing as the negative charge moves from the negative to the positive? Boom. 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 I don't know why I keep saying that. I've never said that before in my life, but you're doing it. Good job. Good job. Increasing. Is everyone understanding that? It doesn't see, remember the chart. Remember we talked about this, it was a while ago, but remember we talked about how the charge in the field doesn't matter. It's just when we're closer near the positive plate, it was always high because it has to do with that gradient stuff. Remember? So that's where that idea is coming from. And that's why it's always high, right? And that's why potential isn't potential energy. That's why potential isn't potential energy, because you can't look it. Yeah, for the positive, it looks like potential and potential energy are the same thing. But when you look at the negative, you go, whoa, wait a minute. These are not the same thing. And you see, it doesn't matter the charge. The potential is always high to low from positive to negative, right? Or low to high from negative to positive. Sometimes you might have to go that way. But either way, cool. Make sense? So we answered the question. It said, as it moves towards the positive plate, is the potential increasing or decreasing? It's increasing. If a positive charge moves towards the positive plate, the potential is increasing. If the negative charge moves towards the positive plate, it's increasing. That's the concept. Cool? You guys all right? Okay. I just want to hear from a few of you. Some of you are probably like, Carl, I don't know when you're stopping. I get it. Okay. Next worksheet. Okay, we're on. I don't know. This one isn't actually. This one's pretty easy. I think we're gonna make it through all these. Okay. So, and remind me if we have time to swing around. There was 2 questions at the beginning we didn't answer, but they're so easy compared to the rest of these. I believe so. That's what I'm looking at. Yeah. So there's like question 2. Oh yeah. I'm sorry. I said next worksheet. That's my bad. Yeah. I mean, just like the rest of. I should have said the rest of this worksheet. I'm sorry. Yeah. Question 2. My bad. No, my bad. Yeah. It sounded that way because that's what I said. My bad. I meant yes. No. You guys are so wonderful. I'm just so proud of you. All of you are so amazing. Okay, so the number 2 says the sketch of the potential graph, and again, so confusion on the terminology, potential energy. So send me an email, okay, and we'll talk about it, because I don't know, were you here at the very beginning? Because that's really the discussion we probably need to have again, because the minute that I show students what potential actually is, it clears up in their head. Like you can see, like we can show you a picture of it. It's not a real thing, but we can show you a picture of it, and then it's like, oh, that's what it is, and it's like, oh, well, that makes sense why we're saying what we're saying now, because that's all it is. So does that sound good? Can you send me an email and then we could talk about it? Cool beans. Promise me that you do. Don't. I'm gonna find you if you don't. Okay, we're gonna figure that out. You're not gonna not know that for the test. Okay, I refuse that to happen. Okay. So he gives us this. Now, again, a lot of this stuff, we can totally use the math, okay? But please know that a lot of this stuff actually can be answered with concept. I'll be completely honest with you, but let's definitely use what he's telling us to do here. So he says this is where it becomes hard because I'm not a robot, but I'm going to do my best. But you all have the pictures, so I'm not too concerned with how perfect this is, but I want it to be. Again, if I have to switch the electric field, I might have to swap around real quick, but for now, okay. But then I might have to change as I start to draw. Okay. He says sketch shows potential versus potential graph by using the fact that the value of the electric field is this, which there's a lot. This thing's telling you a lot, and I'd love to hear from some of you telling me what this says. Sketch the electric field. Or EX versus X, right? The distance, electric field and distance graph on the right at appropriate scale on vertical axis. So yeah. So first of all, there's a few ways. Who can tell me what this tell me a few things about what this equation is trying to tell us to solve this problem. Why does he tell us, look at this thing, use it? It's telling you something. And it's the answer. Why is he saying that? Oh, it's telling us that the electric field is the slope of something. Oh, so you're saying that this equation right here, you're telling me that this equation right here is actually telling me that the electric field is the slope of this potential versus displacement graph. But how did you know that? Are you telling me that electric field is equal to the rise over run of this graph? And are you telling me that the rise is equal to the change in potential? And are you telling me that the run is equal to delta x? Oh, wait, you're right. They are. Huh. Good job. Good job. Good job. Okay. So that is, I mean, please trust me, you can just, if you want to just look at the delta, the change in potential right here. You could say, okay, the change in potential is equal to 10. And right here, the displacement is equal to 1. So that means, let me write that a little bit clearer. So that means delta V is equal to 10 and delta X is equal to 1. So these over themselves tells us that the electric field is going to be equal to 10. So you can totally do it that way, right? If you want to, look at the numbers individually. But keep in mind, like even just doing the slope here, because if you did the whole slope, let's say you just looked at from here, let's say you didn't want to do it piece by piece. Everyone's saying just look at the entire slope. Well, even though here, right, the change in potential is going to be equal to 20, but what's delta X now equal to? Oops, 2. Okay, good job. Oops. So even if we just looked at the entire slope together, which is what everyone's saying to do, which is great, right, we would still see that, this is 20 over 2, which is equal to 10. Right, so that it's still going to be, and if it's the whole slope, that means that it's just going to be this constant value the whole way through. But if you didn't do it that way, you'll see that this is the delta X is 1, the change is 10 for this amount, and then right here, the delta V is equal to 10, right, for this amount right here. And the delta X is still again equal to 1. So even if you did it piece by piece, you would see that it's 10 for this amount and 10 for this amount. Does that make sense what I'm saying? Or do you want me to go deeper here? If you're typing and you have a question, continue to type it and then send it to me and then I'll answer it, okay? But if not, I'm gonna move forward, okay? I'm getting a lot of goods, so that's enough for me to. But please, if you have a question, say keep typing, keep typing. Okay, go back. It's sitting. The question's sitting there waiting for us to go back to. Okay, so number 3 says this sketch shows and this again, remember, I talked about this in terms of concept already. Remember all this up here, the very top? So look at, now it's coming back, right? Look at question 3 here. Question 3 is saying, okay, look at this sketch, but look, there's already, now again, we want to solve for things, okay? We want to, I'm not saying let's not use math, but man, we can just look at this stuff and our concepts will like tell us so much and at least let us know if we're getting right answers, right? And we can see from 6 to 2 that the change in potential is consistent. It goes down by 10 in increments of 1, right? Do you see that? From 6 to 5, it drops from 10. From 5 to 4, it drops to 10. From 4 to 3, it drops 10. From 3 to 2, it drops 10. Do you see that? That is a constant electric field. Automatically in your head, you should be saying in your head, that means the electric field's constant, uniform. Yes. Yes. Sorry. There's a lot of words, but I should be using uniform. Yes. Yes. But again, if we needed to know, right, it would be a disaster if I tried to draw this whole picture, right? But he asked for B, right? Which is right. It's between 4 and 5 and 30 volts and 40 volts. So he says, he says estimate the potential here. But remember, the change of potential really is going to be all throughout this thing. I mean, yes, it's going to, as we move through here, essentially, there's going to be a certain amount of change of, like, we could find the potential at any point, but the change in potential is really the same anywhere in here because that's what these values are telling us, right? So when he puts those letters right in the center, that's great. He's not asking you to use like he's not asking you to use like 4.5 as a number here, and he doesn't want you to use 35 as a number here. He just wants you to say that, the total change in potential. This is answering a lot of your worksheet questions, some of you, is equal to 10, and the change in displacement is equal to 1. And as you can see, that's true as we work our way down, right? If we look at the very next interval, right, this is 20, this is 3, right? So it works, again, this is a disaster if I try to do this, but right, we see that even here, delta x is equal to 1, right? It's constant, the change in potential is constant as you work through here, right? Change in potential is equal to 10 here. So again, even in here, right, we see that the electric field is equal to just like it would be, yeah. New. It's I don't my words aren't wanting to come out right now. Yeah. Thank you for that. Yes.
So is it still uniform? Because if you look at like the first part of it, it's 10 volts. Like that range is 0 to 10 volts, but over 2 meters instead of 1. And then all the other ones are over 1 meter.
Yeah. And the only reason why that one is so large is because, remember, we're at when you get a certain distance away from the electric field, it's going to start to like drop like faster, right? Because of that exponential idea. So yeah, that's all he's trying to show there. But absolutely. But you're saying good things, because everything. So as you can see, yes, exactly, my friend. So from 6 to 5, we see the electric field is going to be equal to 10 Newton meters. We see from 5 to 4, the electric field is going to be equal to 10 Newton meters. We see from 4 to 3, the electric field is going to be equal to 10 Newton meters. We see from 3 to 2, it's going to be equal to 10 Newton meters, right? So it's staying constant all the way through there, right? But then at the very end, when we're really far away, then there's a little bit larger drop, but that's just because we're so far away. Okay, and then so we see that for that last part we have hopefully this doesn't confuse you. That. And right, here's 1, he has 2 here, and here's 0. So we can see that and then he says what is the potential in here. And remember, the change of potential, even though he puts that dot right there, it's really anywhere in there, right? And so and that didn't look the way I wanted to. 0 volts. 0. And then so what we can see here is that the change in potential is equal to 10, right? And here the delta x, right, is equal to 2. So this would be 10 over 2, which is equal to 5. So they're at the very, very end between 2 and 0, right? But that's also a larger interval, right? But between there, the electric field drops to 5 meters at A. Does that make sense? But it's constant all the way through. And then using this top, because again, I didn't draw it all the way out, but we can see that remember, and this comes from a lot of different concepts, we know that where the potential's highest, that's what? We know that that's where the positive charge or the source of the electric field is going to be, right? When we see that high potential. So when we look over at this graph, right, we see that, where the heck did I put it? Where did I put it? There it is. When we look over at this graph, right, we see this is 40 volts, 30 volts, 20 volts. So that must mean that the positive plate must be over here, right? Because the larger potential should also always be closer to the to the positive plate. And then we see that the direction of the electric field should be going this way, right? Because of everything that we've done. So does that make sense? Cool. So what because I'm looking at, we only have a few minutes here. I'm really just gonna, because it's not going to take very long. I'm going to finish this last question, and then that's okay. And then I am. If you can stick around, great. If not, you're not hurting anyone's feelings, okay? But I am going to work through the last worksheet as well, just to get it on in case this does record, and then I can put it up for you all. And I'd love to have all the worksheets on there. But again, I don't know if this recording is going to post. So this is all if everything works good. But okay, so just keep that in mind, because I'm going to talk. But if you need to leave, please, you're not hurting my feelings, and I'm very proud of you. Okay, I'm very proud of all of you. And if you need anything, okay, yeah, me too. And if you need anything, last night, I don't know what happened. I was really tired and I fell asleep. So normally I stay up super late for you, and I will tonight, and I will on Monday. So I'm here for you. Okay, send me emails. Doesn't matter how late, but let's try to get these questions sorted out. Okay. Oh no, it's you, and you're all amazing. Okay. What go ahead, Levi. You don't like, go ahead, my friend. What's up, my friend?
Would we ever have to like estimate if a charge wasn't at the midpoint of a change in voltage?
And that's what I was trying to say, Levi, is that essentially it's not really like about that. Like when we, did I erase it? Oh wait, it should be on this. Oh, sorry, why did I erase this thing? I'm so sorry. I didn't mean to erase this. I erased it. Didn't mean to. So remember what I said when we solved for this change in potential. That was everywhere in here. It's not necessary. I know it looks like he says like right at this point, but essentially that's like when we solve for the change in, but we're essentially solving for even though he's saying right there at B, he's essentially, when we're solving for that change in potential, we're essentially trying to just find the change in potential of this. I'm trying to find a good color here of this particular section right here, because B could, whether it's here, like whether we put B here, the answer is still the same. It wouldn't be any different if we asked you for B at this point, or asked you for B at this point, or asked you for B at this point. Can you see all that stuff?
Yeah.
Okay, so whether we asked you for B's at any one of those points, the answer wouldn't change. The change in potential is still the same.
That's assuming that that's an equipotential surface though, right?
And that's what we started with, right? Great job. That, remember, we not an equipotential surface, but a uniform electric field, and that's what we started with. So that's why we know that this is true. It's not equipotential surface. Okay, like this is an equipotential surface. This is an equipotential surface. Yes. But all right. And like anywhere like in between there would be two, I guess, but they would all be right like that, but we don't really go that extreme. Like the equipotential surfaces are only looked at where the potential changes.
But like for 3 to 0, that's not a uniform electric field, right?
From 3 to 2 it is. It's just 2 to
I mean,
0.
3 to 0.
No. 3 to
Okay.
2 is. 3 to 2 is. 2 to 0 isn't. Again, we already talked about that, right, my friend? That's what the whole bond.
Yeah.
That's what we were saying down there at the bottom. That's that. Cool. All that down there is saying. All right. So let's move forward. Number 4. So he says there's a capacitor charged until the electric field strength inside the capacitor is 5,000 volt meters. Okay, so he's talking about the electric field strength. And again, what was I using? Was I using the wrong? Now I'm thinking, yeah, this should be Newton, not Newton meter, Newton per coulomb. Sorry, I just realized that. I was like, when I saw those units, I was like, wait a minute, did I say Newton meter for the electric field? It's Newton coulomb, because there's 2 ways to write it, right? If you're wanting to get units here. So electric field, if you're wondering where these are coming from, it can be the change in potential over D, where this is meters and this is potential. So that's this, you're right, the electric field in terms of units here would be volts per meter. But we also know the electric field is force per Q. So the units for electric field can also be Newton per Coulomb. Okay. But they're the same when we do some canceling. See, Coulomb is a very complicated unit, and so is Newtons. So when we do all the canceling we need to do, we end up at this unit. We end up at volts per meter. We don't need to see that math in here, but know that happens. I don't want you. The reason why I'm showing you this is I don't want you to think that electric field has two different units, because we've totally given you units for electric field as Newton per Coulomb. And we're now giving you and have in the past given you electric field in terms of volts per meter. And so they're the same exact unit, okay? It's just these are super complicated. And when we write the Coulomb and Newton out in their full form, there's a lot of canceling that goes on, and we still end up at volt per meter, okay? Does that make sense? I just don't want you getting confused about anything. Everyone cool beans with that? Cool, awesome. Okay, so we have this electric field strength, okay? And then we disconnect the battery, and a dielectric we're gonna draw all this, and then a dielectric is inserted. And after the dielectric, we'll call this E little d for electric field with the dielectric. And that is gonna be 1,000 volts per meter. So he wants you to draw this out first, but I'm telling you, even if he didn't, that is the smart thing to do. So he says that you have this, and we'll draw the capacitor really big, right? And it's connected to this source. The battery, the source isn't so important, but there's a source, right? It has a positive side, it has a negative side, and that's how this capacitor is being charged. Okay, so we connect this capacitor to this source, and the capacitor takes on the same, like whatever the change in potential is here. This is a concept I'm saying right now. Will be the change in potential here. Okay, it's a concept that we know. Okay, they'll match if we let them charge all the way up, and right now we are. Let me say that, because man, there's so many details here. Okay, but if we let the capacitor charge all the way up, it's gonna match the potential of the source. Let me say it like that. That makes me feel way better. Okay, and then what happens is that so this thing charges up, right? And then we disconnect the source, okay? And then we add a dielectric. So first of all, he wants us to draw this picture. What's the picture going to look like? And we don't have to make it complicated. Let's just keep it simple. I don't think he's wanting you to go complicated. He just wants you to describe this the new change in potential in the new electric field. So how do I draw? Again, you have to keep in mind that the dielectric is an insulator. So because the dielectric is an insulator, oh, thank you so much. Oh, thank you so much, Tom. I just got a present from one of my neighbors who bought me some tamales. Thank you, Tom. You're the best. Appreciate it. No, thank you. I'm going to eat them now. Thank you. And so, sorry about that. And so, I'm very close with my neighbors. They literally just come in my house. So anyway, well, so I rent from, I don't know if you know Dr. A, she's the anatomy professor at CU Denver. So they're not my neighbors, they're my family. And so I actually live in the cottage. They own a really big house. And so I live in the cottage house that's on their land, I guess is how you could say. So, and I'm their fan. So they bring me dinner and they just walk in my house. I love them to death. Yeah, Dr. A is amazing. And so is the other Dr. A, her husband, and they're both anyway, he's my mentor. And we'll talk about that later. But yes, I love them. And I wouldn't be anything without them. But okay, so back to this. So the dielectric is an insulator. So it's going to polarize. I mean, even if it wasn't, we can put conductors in here. Conductors are polarized as well. Okay, but this insulator, typically it's an insulator, it's going to polarize. And so how's it going to polarize? The left-hand side is going to become what? The right-hand side is going to become what?
The left side will have like a negative dipole, and the right side will have like a positive dipole.
Cool. Exactly. Cool. Exactly. And so what we end up establishing, right? So we have this old electric field here, right? With this change in potential. And then what we do is we get this new electric field with this new potential. And see this potential, you can see it by the picture. This is why I'm saying that it's always a good idea to draw the picture, because it confirms what we're saying. And I wasn't able to say this in SI, and I'm going to say it now because it's extremely important, is that we can see that when we add the dielectric, that not only the electric field decreases, the potential decreases. So when we go to answer this question, like he asks us about if the potential, when we add the dielectric, if the potential increases or decreases, see, we already know that answer. It decreases because the picture tells us it got smaller. Right? So that's one way to go about answering that. But this picture tells us a lot, and that's why he wants us to draw it. And so he says, so that's A, right? That's A. And then B says, by what factor does the charge increase or decrease after the dielectric is inserted? Can anyone answer that? That is a really easy question. Why doesn't it change? Because we didn't do what? Oh, that's the most important part. Good. We didn't attach it to a source of current. So there was no way to, good. There was no way to put in charge or take out charge or anything, right? Like we would have to we would have to add something here in order for charge to be added. There's not, but so you might be saying, well, then what would have to, like, if we added the battery again, if we said now we resupply the battery, because of that dielectric, the plates can now take on more charge. Okay, so they would actually increase in charge, but since we're not reacting, we're not adding the source again, no more charge is added. So B is 0. There is no I'm sorry, the charge stays the same. It's not 0. Does that make sense? Cool. And then C says, by what factor does the potential difference increase or decrease after the dielectric is inserted, or does it stay the same? And so right, first of all, does it increase or decrease? We know right away. So we already know it decreases from the picture. Okay, we're just trying to figure out by how much now. Okay, and so how do we figure that out? Well, we look at what we do is we start with developing an equation for the change in potential before the dielectric was inserted, and then we need an equation for the change in potential, and I'll call that change in potential D, after the dielectric was inserted. Okay, and so that's one equation we could do. We could definitely do that, and that actually is a shortcut that we could take. So I always, when that happens, I actually want to encourage that. So this is what we have, right? This is essentially the change in potential before. This is the change in potential after. Now, where students, yep, you're good. Where students can get kind of confused here is like if the D's cancel. So, but they do in this case. But if you were to do a ratio of the two to find the difference, right? This would be the electric field before the dielectric was added. This would be the electric field after the dielectric was added. So these would cancel. So we see the change in potential is really just a difference of the electric field before the dielectric was added and the electric field after the dielectric was added. So that's 5,000 over 1,000. So that's equal to 5. So that means it decreased by 5. So that's one method to go by. And that is the shortest one. But if you don't like that one, what you can do is you can also use this equation. You can say, okay, delta V, because and the reason why this one's like, I don't know, I would say if you're going with concept, this equation is directly related to a capacitor. This one is, but it's really for any two plates, right? And so, you know, if you're trying to use a concept here and try to connect an equation to the concept of a capacitor, you definitely need, you know, you would want to use the method that I'm about to use right now. But this one definitely works. Okay, it gets you the answer that you want, I guess is what I should say. But in this case, right, this is, so we're gonna use this equation, right, and we're essentially gonna look, since Q doesn't change, only the capacitance is changing here, right? Because the capacitance changes when we add the dielectric. We essentially want to make sure that we have two change in potential equations. One of them is going to be written with the capacitance without a dielectric, and then with the equation for the capacitance with, I mean, sorry, this is without, without, and this is with a dielectric. Okay, and so that allows us to write two equations here. So I need more room. And so what we can, I pinch it off, and then so what we can do is we can say, okay, I got a change in potential before we add the dielectric. So that's going to be, you know, Q over epsilon naught A, and then this D will come up, right? So when I put this equation into here, this comes to the bottom and this comes to the top, right? Does everyone see that math, or did you want me to show it to you? It should be pretty, I think you all are probably pretty comfortable with that after physics 1. You almost have to be, but if not, tell me. Does everyone see how I got these two equations from these over here? If you need me to show you, I will, okay? Because see, what you should know is these equations that I wrote over here, like these aren't on your equation sheet, so you got to be able to get there. But it's just putting these together. Okay, right. I put this one went in there, and then I wrote another one and put this one in there. And so we have these, and so now again, it's literally just doing a ratio again of the change of potential before the dielectric that was added and the change of potential after the dielectric was added. But now, right, it's going to be, so before the dielectric was added, right, that's QD over epsilon naught times A. Now again, we could put this equation underneath here, right, but that's really messy. We also know when two things are divided, we can just flip and multiply, right? So we're going to flip this equation. Oops, that K should be on the bottom. I wrote that wrong. I apologize about that. I don't know why I put that on top. But we're going to flip this equation. And so that means that epsilon naught A, K go up, and then Q and D go down. And then what happens here is epsilon naughts cancel, right? Because those are constants. The areas cancel because you know, the areas of the plates don't change. The distance between the plates don't change, so the D's cancel. And the Q's don't change, so and they're the same, so they cancel. So all we're left with is this K. So we see that this, and this is really the concept. If you read in your book, they're going to tell you that anytime you add a dielectric to a system, the potential and the electric field, this is true for both. This is a concept that we're actually doing on this problem, that both of them, the potential and the electric field, when you add a dielectric, will always reduce by a factor of kappa. That's a concept you can write down and memorize. Like, you don't actually need to do this math, but we're proving it here. And kappa is really just that first answer we had, which is the initial electric field over the electric field after we had the dielectric. Because there's no dielectric for the initial potential, right? The initial potential is before we add the dielectric, so we can't have a dielectric constant in there. That wouldn't make much sense. And then what we can do is then we can let me do this. Like, and then what we can do is we can just look at, right, kappa, just get that final answer, which is going to be 5,000. That's epsilon naught, essentially the initial electric field, over the electric field with the dielectric, which again is equal to 5. So again, kappa is equal to 5, and that's really the concept. Is all you have to do is if you know the concept, you actually don't have to go through any of these equations that we just went through on this question. You say every time a dielectric's added, just as long as there's no charge added, okay? So if you charge a capacitor, add a dielectric, and do not add any charge, it will all, when you add the dielectric, the electric field and the potential will always decrease by a factor of kappa. Everyone cool with that? Cool. Okay, so let's finish this last worksheet is really easy, so we're gonna get through it really fast. So we're almost done. But please, if you have questions, like, ask away, okay? But this one, I just need to find what I gotta erase something. And again, because we went through these worksheets, okay, there were some things that I didn't like directly. I'm going to try, again, these let us talk about a lot of things, but please go back and look at the slides and be like, we didn't talk about this in the review. If you have questions about it, send it to me. Like again, I slightly talked about RMS values, but I didn't get all the way into them, right? But you have questions on your slides about them, so that means they're a potential to be asked on the test. So please send me questions about those if you have them, or tomorrow's SI, we will definitely cover them, okay? Keep that in mind. Tomorrow's SI will back up anything we did not do tonight. All right, so for the potential current and resistance worksheet, he says that, and again, this is where my order, I have an old worksheet, so actually my order is different than yours, so I got to remember that as I read this. I'm just going to do that for the light bulb, okay? That actually means AC current, but I'm just going to call that the light bulb, okay? And then and you'll know that means AC current here in a couple of weeks. No, you're okay. I'm almost done, and like I said, hopefully this posts and you'll get all this. But if it doesn't, and you need something with these worksheets, let me know, because remember, these questions will be on the test. But I'm proud of you, Quinn. Let me know if there's anything you need. Proud of all of you. You're just amazing. That's what you are. Okay, so awesome. So he tells us that this is 6 volts. So the change in potential right here is, I think I had that right. This is the small one. That's the long one. Yeah. And so the change in potential. If it works, I'm going to send you an email directly with it, like with the link. Cool. And remember, when I send that email, if for some reason it doesn't come into your UCD inbox, it will always be in your Canvas. So just check there. Cool. Awesome. Okay. So we know the change in potential here is right. Equal to 6 volts, right? Which another way to write that would be the EMF here is equal to 6 volts. Remember, we talked about this earlier about the EMF being the push. This is pushing the current, pushing it through. Okay, and it's pushing it through that light. right? That change in potential at that battery is working as the push. Okay, it's giving and because it's working as the push, and we know that push and force relate to energy, we know that that push is essentially related to the amount of potential energy that this charge has as it moves through the circuit. Okay, and so just saying some concepts here, but we actually said them already tonight. And so, and we know this. And the other thing to realize, right, is that on this side, this is 0 volts. On this side, it's 6 volts. That's why the change is 6. That's why we say the change is 6 volts, but it's actually 6 volts on this side, right? And it's actually 0 volts on this side, right? Everyone understands that, right? And in fact, even at A, he wants us to say like that's 0 volts there, and we should. Okay. And so what he says is that, and I'm going to make sure I say this in the right order because mine's in a different order, is that he says start at the negative side. So please correct me if this order isn't correct, of the battery. And then he says indicated by A, and then go to the positive terminal. So he wants us to move this way through the circuit starting. Okay. And then he wants us to go this way. Go this way, go. This is the way we're going to work our way through the circuit to make this graph, okay? And then come back this way again, okay? Because he's wanting us to do this graph. And so, cool. So what happens when the current goes from A? So we'll call this A. What happens what happens to the potential of the current? Because that's what he's asking. When it goes from A to B, does it increase? It increases, right? And let's make that number. Okay, so it increases, right? And again, this is going to be kind of sharp, but let's make the point. And then good to B. And then what happens as the current moves from B to C? Yeah, it stays the same, right? There's no change in it. Okay, great. And then what happens when the current goes from C to D? Good, it drops again, right? And so that's what he's wanting you, that's the graph that he's wanting, right? Start positioning. Yeah, so that's what he's wanting, right? I mean, from D, I wrote B. But from D, it wouldn't, right? There would just be a flat line to A again, right? Sorry, I'm writing that in, but he does say like go back to A, so technically you would make an A, and then right. It's zero. It's 0 volts over there. Yeah, sorry about that. I should have totally labeled that. Does that make sense? What? Oh, okay, I'm just making sure. Please clarify if I'm missing something, because like I said, my questions, this is the question that's different than from what you have. So if I'm writing something wrong, tell me. Okay. But really, this is what he wants you. I mean, you know, from D to A, it stays, it doesn't change, right? And again, one other way to do this, and this is what I would suggest to do, and this is what Dr. Ngana would want you to do, is like use color here if you can. And say like, okay, anywhere I have a green current, that's going to be the same potential. And in this case, green means 6 volts. And anytime that I have a blue current, right, that blue current means 0 volts. Right, so you can also use that to make this graph, but it's good to remember he's mentioned about using color, and it helps to like color your currents based off their potentials if you can. But okay, cool. So does that make sense what we're saying there? All right, so then the next question says, consider the sketch, which we have. Are the potentials at point A, B, C, D the same? If not, indicate which one's bigger. So okay, bigger or smaller. Like okay, with the greater or less sign, are currents through points A, B, and C and D equal, if not relate by inequality. So let's start with the potential. Okay, now you have this from this graph, but just tell me. So let's start with velocity at B. Okay, so is that equal to, greater than, velocity? Sorry, potential. Or wait a minute, hold on. He wants us to start at A. I apologize. I guess it doesn't matter, just as long as the signs are correct. I guess it doesn't matter how we start here. I'm so worried about how it starts because the first one is all about order. Right, so VA, let's write it like that. I like that. So VA is equal to VD, and we know that VB, I think that's a much more organized way to write that. Yeah, I like that. And VB is equal to VC, right? But we know that C is larger than D, right? We know that VC is larger than VD, right? So if we wanted to write this all out now, just put all these together essentially, right? We would have VA equals VD, which is, well, I guess in the order I'm going is right, is less than VB or VC, sorry, which is equal to VB. Cool. Sorry about that. I struggled with that a little bit, and I don't know why. Yes. Yes. Good job. Okay, so that's the answer there. And what about current? Does it change, or is it just all equal? He asks, does current, can we rank current like this, is what he asks. Right, it stays the same. So if you wanted to, B is equal to I, C is equal to I, D is equal to I, A. Okay, good. If you wanted to, you could write that though. All right, and then it says in the sketch of number 1, do the electrons flow clockwise or counterclockwise? Do the electrons flow clockwise or counterclockwise in this picture we have? Yeah, so the electrons are over here, right? And they're gonna want to flow this way through the system, right? Towards the, and again, how do you know that? How do you know the electrons want to flow towards the positive plate? Well, how do electrons normally flow? From high potential to low potential energy, right? And they also flow from concept. Another way to say that is electrons always flow. That's another thing that this picture is trying to tell you. Electrons, there's 2 ways to say this essentially. Electrons flow either from a high, naturally, if they're left to just sit in an electric field, they're going to naturally move from high potential energy to low potential energy, but they'll move from a low potential to a high potential always, right? Yeah, I believe. Yeah. From the convention of positive to negative, and the potential being low to high, in that case, versus the change of potential, which is high to low. But what I'm trying to say is these are also trying to tell you that if you're going to have, this is how this picture relates to current, is that if current's going to flow through a system, the electrons are going to flow from high potential energy to low potential energy, or from a low potential to a high potential. And positive charges will always move from a high potential to a low potential energy, or from a high potential to a low potential. That's how the currents will naturally flow, from either a high potential to low potential for positive, high potential, or from a low potential to a high potential for a negative, or both of them will naturally flow from high potential to low potential energy. Does that make sense? How that correlates to this picture as well, that concept?
Would there be any time where the current would not be equal in all those places in the circuit?
In parallel. In
Oh,
parallel.
yeah.
So that's what the great question. And that's where that concept comes into play, right? So we know that just as long as, and if we had like 3 light bulbs in a row, the current would be the same all the way through these, right? But if I had light bulbs that were parallel, the current would not be the same for these two light bulbs because they would have to split. Great question.
Okay, makes sense. Thank you.
Absolutely. Great question. Great question. Okay, so electrons flow clockwise is what we said. Okay, so electrons flow, and CW means clockwise. And then, but then he says, which way does the current flow, right? And current is always the positive charge. Okay, when we always ask you what's the direction of current, we're asking you what is the direction that the positive charge would flow. Okay, and that's, yep, counterclockwise. So the current, right? The current, or maybe I'll write is I, the I flow is counterclockwise. Okay, cool beans. And so that's the answer for 3. Everyone okay with that? Pretty straightforward, but if you have questions, please ask. Does electrons electric potential? Now, we just talked about this. It's on this question. It's on this, again, this question that he's about to ask you is, again, coming from this picture. Does the electron's electric potential energy increase, decrease, or stay the same as it moves through the wire? We just answered this question. And why? What's the concept? Because negative charges and positive charges will always move from a what to a what in a circuit? High
Potential energy.
potential energy, not potential. Remember, that's the one that's backwards. But for both positive and negative, they'll both move from high potential energy to low potential energy. But for potential, that's different. Negative charges move from low potential to high. Positive charges move from high to low for potential. But potential energy, they both, no matter if it's positive or negative, will move from a high potential energy to a low potential energy. Cool. Again, answered by this picture. This picture is there to help you. It answers. Is everyone? Because the reason why I did this is I wanted you to see how to use. Is everyone understanding how to use this picture? Because I hope you find it useful and see how much it's going to help you on the test. Like I said, I mean, I don't know how you all study, but that's how I would try to. When I would have to take tests, I would try to make as many pictures of and they're not maps at all. They're just pictures of like a way that I could see all the concepts on one picture, right? And as you do that as a student, try to do that. If you do attempt to do that, see, that's where you'll also study and you'll get to understand things more, because you're going to have to make that picture. You're going to have to say, okay, this picture has to make sense for the test. And as you develop that picture for yourself, you're going to go through concepts and you're going to make sure everything jives. It really helps you study as well. Okay, so number 5 says the wires below are all made of the same material. Rank the order from largest to smallest. The resistances of these wires in the sketch. R represents the radius of the wire. L represents the length of the wire. Assume R1 in the resistance of wire R1 and the resistance of wire 1. Okay, he's just saying R1, R2, R3. And then explain with help of a mathematical equation that relates resistance of a wire with size of the wire. So again, I am not an artist, so this might be a disaster, but what you all have the pictures in front of you. Let me try to do my best here. But he does, like, there's some. Okay, so, and he says that this is good. So these are supposed, and I guess I relatively did that again. I'm not an artist, but these have the same length. I should have done that. Let's not waste time on a picture, but they're both the same length. Okay, I'm just not an artist, but they are in the worksheet. And then he says that this has an R radius. This has the radius here is 2R, and this is also a 2R. Again, the radiuses, these are equal, but I'm not an artist, so it doesn't look that way, but they are on your picture. And then right, and he says, right, this is pipe 1, this is pipe 2, this is pipe 3. And then he says, calculate the resistance between them using an equation, and Jessica already gave us that equation, right? And again, if you don't, should you memorize this equation, or where can you find this equation at? Yeah, it's on the worksheet. I mean, not the worksheet, the equation sheet. Yes, I said the same thing. Yes, it's on the so what we see here, right? We're trying to look at the resistance, and so the essentially the resistivity is all the same for him. What he's trying to say is that really the resistance is really based off the lengths and the areas. So before we solve this equation, what is area in here? Because this is where I see students make the mistake. What is area equal to in here?
Pi r squared.
Yeah, it's just the area of a circle, right? Because that's all this is right here, right? That's all when we talk about area, right? And then L is length, but area is the yes. I don't think I need to explain that any further. Okay, so good job, absolutely. So when we do this, right, we got to make sure that we don't, like, this equation's a little deceiving. So it's probably better, right, to write this equation in terms of like L over pi r squared, right? Because see, this R now, right, is going to start to make a difference. That's where that R comes into play. And especially when it's squared, right? That's where it really can, I forgot to write, this is 2L. I just noticed I didn't have a length there. Okay, so let's do this. I'm going to need that space right there. So right, for pipe 1, right, the resistance is going to be, again, the resistivity is the same for all of these. We're not, that's not going to play a factor here. It's really what's ending up playing the factor here, but it's going to be in the equation everywhere, but it's really this, it's going to play the factor. So what is L in this case? It's just L, right? And R is just R, right? So essentially this equation doesn't change. That's going to be the equation for that. You might be saying, okay, what's the point of that? Well, we got to get the other two equations for that equation to make any sense. But that is the resistance for that. The thing you can say is that that's the resistance for that particular wire. And then for this next one, right? Again, the same thing, but what's L going to be? What's L going to be? Just L, right? Because that's what's here, right? But what's the area going to be? It's going to be pi squared 2r squared, right? And so what does that mean? That means that this is going to be, again, L is going to be on the top, but this is going to be pi, right? This is a weird way to write. We're going to have to write it again, but right? The pi is going to be there. The 2 squared is going to be 4. Let me say it like that. And then r squared is just going to be r squared. And then, right, when you look at this, we can rewrite this because that's a real, that you look at that and it's like, I can't tell what that's telling me. So we can pull that 4. It's sitting on the bottom, but actually, if we pull it out, it's actually 1/4, right? If we take this and just bring it out here, right, it's 1/4. Is everyone okay with what I just did there? and then so that's our so we have these two equations. So now we can kind of see something already. What is this equation telling us? It's what? This wire has more or less resistance. Oh, I forgot the pi. Yeah, less. Good. And then we'll do the same thing. Sorry, I'm gonna write that. There's more room over there somewhere. This is 2R, right? And so want to do the same thing for this last one. Again, we start with R. What's L gonna be? Well, in this case, it's 2L, right? That's what L is in this case, right? And then R is going to be 2R, so that kind of like we did the last time, right? We're going to have this pi and then this 2R squared, right? And so when this one's going to take a little bit more math. In fact, I'm going to need this space, but I'll redraw it here in a second. And then so when we do this work, right, we see that this is 2L on top. I'm just going to work with the numbers right now, and then I'll bring everything back in, the pi and the resistivity. Okay, and then we have 4R squared, right? So what are the 4 and the 2 going to do? Kind of reduce, right? That's the word we use there, I guess. And so it's going to turn into 1/2, right? So we know this is going to be R is equal to 1/2 L R squared. And then we can add these guys back in. There, right? The resistivity and the pi were constant, so we kind of, you can, when you have constants, you can set them aside for a second. Like the derivatives of those will all be 0, so you can always set them to the side. Oh wait, that's wrong class. Constants you can always set aside, okay, when you're doing this. And then and then to write this out, we can oh, my pen shot. This 1/2 again we can pull out here, and then write resistivity, and then times L over pi R squared. So that's the equation for this, and that's R. So and I forgot to label these, but that's R3. This is R2, and this is R1. So what is this saying? Who's large? How do we rank these? R1 is the largest or the smallest? Because it doesn't have any like 1/2 or any or 1/4 in front of it. Yeah, that means it's the largest. Cool. And then who's the second largest? The one where the resistivity is 1/2 or a 1/4? Right, R3, right? So this is large. R3 is smaller than R1, and then R2 exactly is going to be the smallest. So there's our answers. Cool beans? All right, and then that last question's really straightforward, but let's go ahead and just answer it since we're already here. Household electric. So what is he wanting you to do here? He says that you right in the US, right, we know that the potential into our households are 120 volts, right? And for Europe, 240. And by the by, these are RMS values. We don't need to tell you that because we're not going to deal with that. But remember, RMS values are the things that come into our house. In fact, I think like the actual potential is like 160 or something, like that's actually from the power plant. But the effective, the RMS value, the potential that's used in circuits in your house is 120 volts, which is the RMS values or effective values. Essentially, what the AC current would look like if it was just a DC current. Okay, just wanted to cover the concept that he was wanting you to see here. That he's always trying to talk about a lot with one question. And then you want to design a 60 watt bulb. What is this variable that he just gave us? He said this is a 60 watt bulb, but what is this variable? Good. And so good power. And so he says what should be the resistance of the coil in the bulbs? Is it the same? And so it is like we're not going to use RMS values, but you're right. Like we can write all these since they're all RMS, we're like RMS. We can say we're not doing that here. He's not specifying that right now. And like I said, I really think I don't because I don't even know if there's an actual question about RMS on your slides. He talks about it, but I don't know if there's questions actually about solving for RMS, because that's actually a totally different. We're going to get to that chapter. There's going to be an entire chapter dedicated to like RMS values and max values, max amplitude values. So yeah, he's just asking about Pmax, which is fine to ask you about now, but definitely RMS values would be kind of a stretch to ask you about right now, because there's we really technically haven't explained them to you. There's a whole chapter dedicated to that. We'll get there in like 3 or 4 chapters. But he asked about the resistance. What's the equation that associates the power with the potential? Good. Well, right when we, so right. Let's start with the. So we know right. There's this equation that's power that's v squared over r, right? And then yes, and then we can solve this because we're trying to find out the resistances, right? So the resistance, right, would be v squared over p. And then I mean, this is plug and chug, right? You're going to do one for the U.S. Right? This is going to be the resistance for the U.S. You're going to do the resistance for Europe, and you're going to see they're not the same. Obviously, how can 240 over 60 and 120 over 60 be the same? So that sounds, I don't know. I don't think I have these numbers in order, but I might. Are other people confirming? Because that's going to take me. Okay. Yeah, I'm sure I have this number somewhere, but if someone else is confirming, then I'm not going to. Okay, cool. All right. So there we go. So we're done with the worksheets. All right. Okay. So well, you may feel that way, Levi, but what if this is the question he asks you? I mean, there's a lot of concepts going on here as well. So you don't want to think that way. Like, you definitely don't want to try to get in Dr. Dungana's head and say, oh, he's definitely going to probably ask me this question versus that one. I would not do that, my friend. To him, they're all equally important. He doesn't. Oh, you're so welcome. I'm proud of you all. Okay, I'm proud of you all. Okay, and again, please let me know what I can do for you. Send me emails. Let's get you anything that you need before the test. Okay, and like I said, if there's anything we didn't talk about today, it will be covered in SI tomorrow, and I'll send out the reminder for that. Absolutely. No, I'm proud of you. You guys are why I do this. So thank you. I'm gonna miss you because I'm gotta go get my PhD now. It's in Augusta, so I won't be able to do this anymore, and I'm gonna be sad. but you're all amazing, and let me know what you need. Okay, I'm here. I'll still be y'all. My UC account will be open. If you guys need help with MCAT setting or something, you better hit me up because I'll totally help you.
Thank you, Carl. I really appreciate it.
Absolutely. No, I appreciate you all. Thank you for working so hard. One step closer to my goal. Yeah, well, hopefully it shouldn't be hard. PhD is interesting. You're so welcome. And if you have questions, please ask. Sorry, I forgot. You're more than welcome to hang out and ask questions. So if you have them, ask them. Because I think some of you, we were going to chat afterwards, but then that was before I had, have a good night. That was before I had decided that I was just going to do all the worksheets. So everything we were going to chat about was, I think, about the worksheets. So I think we covered everything. But please, if you have questions, ask. I don't have a ton of time, but I can talk a little bit because I got to get this recording. Actually, stop the recording and see if this is going to work. But please ask questions because I got to do this anyway.
So